Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. Hello, this is Frank Harrell. I want to welcome you to the Regression Modeling Strategies course. I see that we still have some people logging on, so I'm going to give it another minute before we formally start. Okay, let's get going. I'm Frank Harrell. I'm a professor of biostatistics at Vanderbilt University in the Department of Biostatistics in the School of Medicine. Very pleased to be offering this 3.5-hour regression modeling strategies course today. We have a really excellent turnout, and I'm very glad you're here. This platform is still a little bit new to me, so I hope that shortly we'll be able to figure out how to make it maximally work for you to be able to interact during the course. This course is really thriving on discussions and questions and controversy. And so I hope you will be really free to speak up, to unmute your microphone at any time or put a question in the question and answer channel. I may not check that channel very often, but I'll try to check it periodically. So between the question and answer channel and you're speaking up with your microphone, let's have as much discussion and questions as you want, so that this course helps you as much as it possibly can. So I'm going to share screen. You should see the cover of the notes that we're going to be using. And at the top of that are 5 web addresses that are going to be key for this course. The top one is where these notes are found. Now, this is a very large set of notes that's from a full 4-day course, as well as a full semester course that I just finished teaching at Vanderbilt. So there's a lot of material for you to refer to, and we will not be covering but a fraction of the material. So don't be too put off by the volume of material there, but that rms.pdf is the PDF that we're viewing. I will ask people who are not intending to speak to mute their microphones, please. The second URL is the central web address for the RMS course. It links you to a lot of other material, including study questions and other handouts that might be useful. And then the next link is to the RMS package. So it gives you some vignettes and documentation about the RMS package. And the link to the right of that, the RMS intro.html link, is an introduction to the RMS package, which also serves as an introduction to ordinary linear regression. So some of you may want to look at that one if you really want to use the RMS package. It'll give you a very gentle introduction compared to maybe some of the more advanced examples we'll see today. And then the last address, the RFlow, is brand new. So I just finished that book really about a week ago. And that is really putting this in the context of a larger workflow. So not just modeling, but especially how to get data ready to analyze, how to check data, and especially how to do a lot of descriptive analyses that are really not modeling, but analyses that are very helpful in understanding the data. And sometimes these descriptive analyses are ins and of themselves. So, so you might look at that new electronic book, the R Workflow. So the main notes that we're going to be going through, the large set of notes are here, and there's some links written here, including links to a 4-day course, including ways to obtain videos of that long course if you wanted the full thing. And then there's a link here to datamethods.org/RMS. That is our main discussion board for the regression modeling strategies course. And when you go to that particular link, that is the page on our discussion board for discussing software issues. But at the top of the link, it has a lot of other links to the particular chapters of the regression modeling strategies book and course. So if you want to ask a question offline, not during today, but later, datamethods.org is the place to go, and just navigate to the top of that page. And that will tell you how to get to the individual chapters. Like if you had a question about spline functions or about model validation, there'll be specific chapters for that. So take a look at that. And then, of course, stats.stackexchange.com is really the world's busiest question and answer site for statistics and machine learning. And that's got so much helpful information, it's hard to know where to start, but I'm always getting help from stats.stackexchange.com. So this is an outline of the course that we'll be covering a piece of. It covers a lot of different material related to statistical modeling and uses of statistical modeling and case studies, and a lot of material about model validation. So you can take a look at that to see what else you want to read outside of what we're covering today. And I'm going to get right into the course philosophy and cover just a little bit of this so you know where I'm coming from. So what is modeling? It's an endeavor to transform data into information, and information into either prediction or evidence about what generated your data. So it's kind of a general definition of statistical modeling. And besides giving you formal analysis, models are also the best descriptive tools that I've found. And the reason for that is we try to do descriptive tools like scatter plots. You know, that's great if you have 2 or 3 variables. You could color code your points to show the third variable. But once you get into adjusting for the effects of other variables, the regular descriptive tools quit working in higher dimensions. So you can use a model to describe a relationship, whether it's linear or nonlinear, and that is going to allow you to adjust for background variables while you're looking at the descriptive results. So that's impossible to do with things like stratification or subgrouping. Satisfying model assumptions improves precision and power. That's probably the least controversial thing we'll talk about today. This is a little bit different to some people. So a lot of people are into the classical approach where you have a fairly simple model and then you do some diagnostics to find out where the model goes wrong. I really don't like that approach very much because it's extremely subjective, and a lot of the model diagnostics are not actionable or not directly actionable. So the philosophy that I've taken is to make the model fit step by step to the extent possible, so there's fewer diagnostics that you need to run. And so instead of postulating a very simple model and find out what goes wrong, we're going to postulate a model that's more likely to fit. And that's actually going to give us better statistical results, and it's better in a number of other ways also. But we have to be wary of changing the model in reaction to observed patterns, because if you do a diagnostic plot or something more like we're going to be doing with models, you can't just keep changing the model in reaction to what you see, because you'll make the model too good to be true. So that is double dipping. And we know that anytime you double dip, you're going to get some false confidence in how well the model works. Graphical methods are wonderful. If you don't marry them to inference, they can be misleading. You can have some beautiful graphical trends where the confidence limits include every possible trend, and you're focused on the trend and the point estimates. that's not going to be very safe when the confidence band includes thousands of other possible trends. Overfitting is a big problem unless you're into web data, where you might be getting data off of Netflix or some other data source that has almost unlimited data. Those of us that are in social sciences or biomedical sciences and a lot of other areas, we don't have the luxury of having millions of subjects in our data. And so we are really at risk of overfitting and overinterpretation. So we have to be very careful about that. And overfitting is one of the most common problems in statistics and machine learning. And then software is important. So a very smart statistician I know made a prediction 20 years ago that there would be no coding by this year. There would be no coding. People would use menus for all of their analyses. And really the exact opposite has happened. For two reasons. We need things to be reproducible, and scripting analyses is really the only way to make them reproducible. The other reason is menus can't keep up with statistical developments. So there's so many methods being developed, and to implement a menu to run every possible method is just not feasible. So languages such as R and Python have become ubiquitous and have created a lot more need for coding than we ever had before. Carefully fitting an improper model is better than badly fitting and overfitting a well-chosen one. That's going to seem like a very odd thing, but some people obsess over the model fit, and then they do everything else wrong, such as analyzing 35 events with 30 predictor variables. That's just not going to work. So whether you chose the model correctly or not, if you're trying to fit 30 parameters from 35 events, everything is going to backfire. We're going to emphasize methods that work for all types of regression models, so you have one thing to remember, and it creates a lot of flexibility. And then what you do with data does make a difference. I've seen lots of studies where it was $1 million or maybe a multi-million-dollar study, and somebody did a $100 analysis. And they made the study really worthless. So you can ruin great studies and great data with analyses that are subpar. The bootstrap as well as cross-validation are breakthroughs for statistical modeling and validation. We use those a lot. Bayesian modeling is now ready for prime time, and this allows us to open up an amazing number of new capabilities in terms of the flexibility of models, as well as incorporating data, non-data knowledge outside of the data set. And so we'll talk a little bit about Bayesian methods, but we don't have time to talk about it very much. But the software developments, especially with RSTAN and RSTAN-ARM and BRMS, the software developments are incredibly impressive in the last 5 years. And that's opened up Bayes for even the most routine sort of analyses that you're doing. And some real advantages of Bayes is you get exact inference, whereas most of the things we do are rough approximations that assume normality. And Bayes doesn't need to assume normality anywhere. Even in a basic binary logistic model, you can have very inaccurate confidence intervals using standard methods, whereas Bayesian methods can give you exact credible intervals. It's also a very rational way to account for model uncertainty and gives you direct inference, so you can get evidence for all possible values of an unknown parameter that generated your data. Also gives you the most accurate way of dealing with missing data. And then a good overall strategy is to decide how many degrees of freedom you can spend or how many parameters you can estimate. Where should those parameters be placed in the model? And then you estimate those parameters or spend the degrees of freedom without any regrets. And there's a companion book to my book, Regression Modeling Strategies, which is Clinical Prediction Models by Ewout Steyerberg, which is a really phenomenal book, which goes into a lot of detail about model validation, includes a lot of simulations and a lot of excellent graphics. So I highly commend that book to you. So we're not going to cover much in the introductory chapter, but to put it in context, there's at least three things that we do in statistics. There's formal testing, there's estimation, and prediction. Prediction is fairly general, and these things are all interrelated. But estimation means, say, you're estimating the effect of increasing age from 20 to 30. So that would be an estimation problem. Hypothesis testing would be, is the association between age and disease, is it a flat line or not? So testing for association is testing for a flat relationship. That would be no association. And then prediction, everybody pretty much knows what that is. So statistical models really give you a general way to handle all three of these things. And models generalize tests. So once you know regression, you don't really need ANOVA and you don't need a two-sample t-test. You also don't really need the standard non-parametric methods because those are just special cases of the proportional odds ordinal logistic model. So the big course notes spend a lot of time with ordinal regression models because they're so general and they're so robust. They don't require you to know how to transform the dependent variable, which is a big plus. So you don't need special cases if you know what model encompasses the special cases. This is more well appreciated that the log rank test is just a special case of the Cox model when there's no adjustment covariables and you're comparing two groups. So you don't really need the log rank test anymore since the Cox model exists. And models allow you to do a lot more than what you can do without models. So you can get all kinds of estimates, you can get adjusted effects, and so on. And models have been applied in uncountable ways that you have heard about, no doubt. So models are used in every field. This is one of our biggest challenges today. And this is where machine learning got started on the wrong foot, and it's really hurt machine learning to a tremendous degree to this day, that there was a misunderstanding about prediction versus classification. So a lot of machine learning experts are doing classification because they understand it very well, and you don't have to understand probabilities fully to do classification. So I think of a classification as sort of a forced choice. I'm going to classify something as, let's say, a letter V, or it's not the letter V. That would be a very good sort of classification task when you're recognizing handwriting using a visual pattern recognition method. So to classify a letter that's handwritten as a V or not a V is a classical pattern recognition task. But in other fields, such as predicting the risk that a customer will be dissatisfied with a product, or what's the probability a customer will buy a product, what's the probability somebody will default on a loan or default on their, they can't pay their credit card bill, that's when probabilities come into play. And so what happened with machine learning, because classification was easier to deal with, people started developing classifiers and not asking if that was really what needed to be done. So in the vast majority of situations, a classifier is not what you want. A classifier is what you want when you're in a hurry and there's very little uncertainty. If there's uncertainty or you're not in a hurry, then what you really want to do is to estimate tendencies. So a batter comes to the plate in a baseball game and the announcer doesn't say he's going to get a hit. So the announcer is not going to classify the batter as getting a hit this time. The announcer is going to say the batter is batting 320. So without knowing anything else, we would say the batter has a 0.32 probability of getting a hit. So what we're interested in is tendencies and not making a classification, just as in rainfall forecasts, we don't say it's going to rain today or it's not going to rain today. We give the risk. So outside of visual or sound pattern recognition, classification really represents a premature decision. And one of my most popular, probably my most popular blog article that's a link to here on my blog, fharold.com, is an article trying to separate prediction from classification. So as I mentioned, this has held machine learning back to a tremendous degree, and there's a lot of people who understand machine learning who still don't understand prediction is distinct from classification. And then they ask questions on stats.stackexchange.com like, I've got a data set with 100 diseased and 100,000 normal people. How do I balance the data set? Because my classification doesn't classify anybody except as non-diseased. And so they get a lot of answers to that question, basically saying, if it's 100 with disease, 100,000 without disease, you can't use a classifier. It's not meant for that. The best you can do is to analyze the tendency for somebody to have disease, and that tendency is just a probability. So this just goes into more arguments about how classification gets you into trouble, and how it loses a lot of information and represents an artificial forced choice. And so one of the ways to see this is sometimes the best thing that an analysis can tell you for a given, let's say a given customer, you're trying to say, what's the tendency of this customer to buy a product? The best output of the analysis might be, we don't know. So we might say the probability is between 0.6 and 0.4. So it's really in the uncertain range. We don't know. We would need more data to tell you what that customer is going to do. So to not just say the customer is going to buy or not buy, but to say, we don't know, we need more data before we can make a decision. That is one of the best outputs of an analysis you could possibly get. And classification is not able to do that. It just does a forced classification on everyone. So once you start analyzing prediction, risk prediction, using risk prediction, not using classification, you can bring in the loss or cost or utility function, and that allows you to make an optimum decision. So there's no way to use a classifier to give you optimum decisions unless you know the utility function, and the utility function is applied to the predicted risk to give you an optimum base decision. So a lot more to this, and there's a crash course here in formal decision analysis. And then there's a kind of a side comment that because of these considerations, receiver operating characteristic curve analysis is really misleading. So once you study formal decision analysis, which has a long history, and we don't tend to teach that in school, when you study it, you'll see that there's no point at which a receiver operating characteristic curve has anything whatsoever to do with a decision. And so it just doesn't come into play because the points on the RC curve are the wrong probabilities for making a decision. They are backwards time probabilities, such as a probability that for those that had the disease, they had a biomarker greater than a certain cutoff. So that's of no interest for a decision maker who wants to know what's the probability somebody with a certain exact value of the marker is going to have disease. So I think we may have one question in the question and answer. What kind of statistics to build a model step by step would you suggest? That's, Tim, I appreciate the question. That's exactly what we're going to be going through today. So hold that question, make sure it's answered, and if not, we will cover that in more detail. But that's really our goal today, or the step-by-step things that you need to do. Yeah, Libby said in the chat, shout out to decision scientists. I couldn't agree more. And there are just not enough of them. And somebody wrote a wonderful article, I think it was in the New York Times. If you ever wanted to teach high school and middle school kids, one of the most valuable things they could ever learn, it would be how to make decisions. We never teach that. So how do you actually do decision analysis, and how do you make better decisions? Super important. We tend to ignore that field as much as we possibly can. Okay, more issues about classification and how that's different from risk prediction. Let's see. Then there's a section on planning for modeling. This is very subject specific. You'll need to see in your area of application what sort of data you need. One of the biggest mistakes people make in analysis of data is they look at what data are available and then they see what model they should fit or what machine learning method they should use. That's totally backwards. So what happens time after time is they will look at the data set, they know what variables they can analyze, and they quit asking the question what variables are needed. So if you have biases in the data, you have to think hard about what variables to collect that would allow you to adjust for the biases. And if you just analyze the data that are available without asking that question, you're going to be coming up with analyses that are not worth very much. And so these questions have to be asked early and often, and not just rationalize that the data that you happen to have access to are adequate. Sometimes the very best outcome of a project is to abandon the project and look for a different project. So having the right data, you just can't say enough about how important that really is. So there's a lot of considerations about what to collect in the data that we don't have time to get into, but in your own field, this is in health outcomes research. This is a general list of what sort of things you need to capture about people who may have a disease, or people you're trying to prevent them getting a disease. So these are very important dimensions. Think about your field. What are the dimensions of the problem and what are the decisions that are being made? So if people are branching out and getting put in different bins because of different decisions, you need to know what the decision points are. For example, if people are getting assigned to different treatments because of how clinically unstable they are, you need to measure the clinical stability of the patient. Otherwise, you'll never be able to adjust to compare like with like. Rob is asking, are other people seeing slides? I hope everyone is. Yes, people are answering yes. Rob, I hope you can get that figured out. So this is just all important. You can't really make chicken salad out of chicken shit if you have really bad or highly incomplete data. Then there's a choice of the model. This is one of our most mysterious things, and we don't spend enough time on that in today's course. But the model that you choose needs to match the structure of the data. So somebody wrote a paper saying if you have binary outcome, it's okay to use least squares. That was a paper in the economics. Well, it's not okay. So if you have binary outcome, you don't want to use least squares because you'll get negative probabilities, and that's just not mathematically kosher. So the model needs to match the structure of the data in terms of the measurements and also the structure of the problem. Is it a fast developing problem or is it a long-term thing? So that's going to dictate what kind of model that you might be fitting. Of course, we like to use robust models. And then this is really the skeleton in the statistician's closet, which is model-driven, data-driven model specification and model uncertainty. So what happens if you try a lot of different models and then you compute R-squared, p-values, regression coefficients, confidence limits? If you calculate those as if that was the only model that you tried, you'll be wrong in every way. So your standard errors would be way too small, p-values would be too small, R-squared would be too big, regression coefficients will be biased. And so this is maybe a place to put this image. There's something called, I think it's called the sharpshooter's fallacy, where somebody shoots the side of a barn and then they go draw a circle around where the bullet hit, and then they tell their friend later they hit the bullseye. So that's really also called getting a free lunch, having your cake and eating it too, and double dipping. So those are all terminologies for similar things. So if you're doing double dipping, so you're using the data to tell you how to use the data, such as doing stepwise variable selection. So if you're using p-values or AIC to tell you which variables to include in a model, that is really going to backfire in many different ways. And the biggest single way it backfires is you will have false confidence in the results. Your confidence limits will be too small because your standard errors are going to be too small. So you can get around that, or at least find out how much damage was done, by using the bootstrap to repeat all the analysis steps as if they saw the data for the first time. They're seeing subsets of the data. So if you repeatedly sample from the data and repeat your analysis all over again, repeating all the steps, including anything that made you select the model and select the variables, the bootstrap will tell you how much damage you've done. It doesn't fix the damage, but the bootstrap will document the damage, and it will allow you to get standard errors that are much more realistically large. So this is a way to tell you how much double dipping you're doing or how much model uncertainty you have. And so Yi had this method of quantifying model uncertainty. Here was a case where you have 22 observations, say 22 customers, and you had 20 candidate predictors, and you do a forward stepwise regression and get the best 5 variable model. By Yi's method, the generalized degrees of freedom is 14.1. So what that means is going through this process of torturing the data to come up with a confession of 5 variables that are predictors, it has the same reliability as pre-specifying a model that has 14 regression coefficients in it and not doing any stepwise regression. So the volatility of this process is equal to the volatility of estimating 14 coefficients plus an intercept in predicting the results on 22 subjects. And 14 parameters is just too many by far to fit with 22 subjects. If you're doing recursive partitioning or classification and regression trees, and you have 10 candidate predictors on 100 customers, and you came up with 19 branches of the tree, the generalized degrees of freedom is a whopping 76. So that means that the volatility of this tree is equal to the volatility of pre-specifying a model that has 76 coefficients in it fitted on 100 subjects. And you know that's going to be extremely volatile and unreliable. So whenever you're fitting a tree, this is why people cannot validate what you do, because everybody will get a different tree with different data sets, even if it's from the same process. It's just not a very reliable way, which is why people don't use single trees for prediction. They use random forest, bagging, and boosting. But that also has to do with why random forests have some of the worst overfitting that I've ever seen, unless you spend like weeks tweaking them. So we may get back to that later. So this is setting you up for what happens when you're double dipping. You have model uncertainty. Here's a simpler example, and it really shows the difference between the Bayesian and the frequentist approach to things. So let's say you're doing a t-test to compare 2 means. Well, the regular t-test assumes equal variance and a normal distribution for the data. And we typically examine the 2 distributions to decide whether to transform the outcome or to switch to a different test. And we sometimes examine the 2 standard deviations to see whether we have a common standard deviation or whether we need to use the Welch t-test. Now, these are all part of model uncertainty. This is a kind of double dipping that will alter the operating characteristics of the t-test in your final step. And your final confidence interval is conditional on the final choices being correct. So if you're using something that assumes normality, you're assuming normality is true. If you're assuming equal variance, you know that's really a true assumption. So you're ignoring model uncertainty, and the confidence intervals will have the claimed coverage if those assumptions are not, only if those assumptions were true, and in other words, if you got lucky. So what does a Bayesian t-test do? You add, sorry about the typo, you add parameters for what you don't know. So with a Bayesian t-test, you have a parameter for the variance ratio, and then you allow the data to have heavy tails by not assuming it's normal, but you assume the data come from a t-distribution. And I've got a fully worked out example in another set of notes that goes through this. But basically, when you're done, the credible interval for the difference in two means, see if I say anything else there. No. The credible interval for the difference in two means is going to be a little wider than if you assume normality and you assumed equal variances. And it's going to be wider by exactly the right amount. And the other nice thing about the Bayesian approach is when you're done, you'll get a uncertainty interval for the ratio of the variances, and you'll get an uncertainty interval for the degree of normality of the data. And you can actually get a posterior probability that the data come from a normal distribution, which is essentially the posterior probability that the t-distribution you're using to model the data has more than 20 degrees of freedom. Because by the time you get to 20 degrees of freedom, the t-distribution looks a lot like the normal. So you can actually find evidence for normality instead of assuming it. And instead of getting burned with falsely confident results, such as confidence intervals that are too narrow, we're going to get the right uncertainties by not assuming normality or equal variances. All right. So that's probably already a lot to digest. So be thinking about what questions you would like to ask by speaking up or putting something in the question and answer box. So we're going to spend more time on model fitting and model validation than on anything today. So we're going to start to get into our model fitting chapter 2 in the notes and in the book. And so when we're using regression models, we can capitalize on a lot of good features. We have efficient estimation methods such as maximum likelihood. And when your problem is such that additivity is predominant, statistical models turn out to be probably the best way to analyze data. So what do we mean by this? So let's say you're predicting lung capacity. Well, lung capacity is going to be a little worse as you get older. It's going to be worse if you smoke. It's going to be worse if you've lived in poor quality air for 20 years. These things could sort of multiply each other, but they may be approximated very adequately by assuming additivity. So we're going to add some, we're going to subtract some lung capacity for how old you are and how much you smoke and what is your air quality that you breathe normally in your city. And the idea that the effect of age kind of adds to the effect of smoking and adds to the effect of air quality is not very far-fetched. And in a lot of data sets, it's a very adequate approximation. So when the effects are predominantly additive or there are not many interactions and you know the likely interacting variables in advance, regression will usually beat machine learning because machine learning doesn't really give favoritism to additive effects most of the time. It allows interaction tests to have sort of equal opportunity. And because there's so many interactions, if you had 10 variables and everything is linear, you have 45 two-way interaction terms. That's a lot of terms to entertain. That takes huge sample sizes to fit those interaction terms. And so if you allow the interactions to be a priori just as strong as the main effects, which is what neural networks typically do, you're going to need an enormous data set, or you're going to add instability by looking at those interactions. And once you go to third order interactions, fourth order, it just gets worse and worse and worse. With regression, you can separate the effects of variables. You can do hypothesis testing. You can get a deeper understanding of uncertainties, such as confidence intervals for a slope. You can get confidence intervals for predicted values, and you can even get simultaneous confidence intervals. So what is a simultaneous confidence band or region for the whole relationship between age and blood pressure over age going from 20 to 80? So we can get simultaneous coverage across that whole age range. Let's see. Michael had asked an earlier question I may have missed regarding dimensions of data to collect. Do you default to using all or most of these dimensions when conducting a patient outcome study? I would say those may not be sufficient, and sometimes the list is too big. And one of the things that is a little bit troubling to me is that even when you're working with great investigators, there's certain important variables that they don't feel comfortable collecting because maybe the scale for measuring those variables has not been validated. And I think I would rather have a non-validated scale than to omit it entirely. And where that matters the most is when you're studying something like disease. Most diseases have a matter of severity. And if you don't capture the severity of the disease, say you just called everyone diabetic, whether they were insulin dependent or not, that would be an example. So if you just label diabetics as diabetic and you don't capture the severity of the disease, you're missing a tremendous amount of explainable variation in the outcome. And so I see even with good intentions, we're not always getting those 11 variables, but the extent of disease being studied, if you're in a medical study, is one of the most important things to get that we're not doing a great job on. Now, this is what a lot of epidemiologists use, is stratification. And stratification is really setting you up for a lot of problems, especially confounding, unexplained variation in the outcome, because stratification is disjoint subsetting. So if you subset people into male and female, and that was the only variable you had, that's still an approximation of an underlying continuous process, but it's a better approximation than a lot of things we do. If you called people obese or not, and you just said, is their body mass index greater than 30 versus less than 30, that is really going to give you an invalid analysis. That's going to pretend that obesity is like falling off a cliff, and it's nothing like that. And so when you stratify a continuous variable, everything goes wrong. And we'll be spending a lot of time talking about that. You're setting yourself up for failure. So stratification doesn't work except in a very special case where you have like one or two categorical variables and no continuous variables. Let's see. Trees, we talked a little bit. Machine learning. So machine learning are things like random forest, bagging, boosting, support vector machines, neural networks, and deep learning. And deep learning is just a new terminology for neural networks. There were some leaders in neural networks said, if we call it neural networks again, people are going to assume it's like the last time we pushed it and it didn't really take off. So, neural networks in its third birth right now. And so they relabeled it as deep learning the last time as a PR move. Of course, they did add a lot of improvements, including being able to go deeper and having better tuning and better algorithms in general, but it's really at its heart is still neural networks. And so the advantage of neural networks, it allows for higher order interactions, and it doesn't require you to pre-specify interaction terms. Now, whenever you have higher order interactions, the sample size required is huge, or the signal has to be so clean that you can get by with a smaller sample size. So that is a real necessary thing to remember when you're thinking about machine learning. So when does machine learning really excel? Well, it excels when you're doing visual and sound recognition, or you're having a machine algorithm learn to win at Go or chess or some other game. So what distinguishes game playing from the kind of data that we see in the medical world is with game playing, there is an infinite signal to noise ratio. So you have rules that can't be violated. You have no measurement error, and you have a clear winner. There's an algorithm to declare the winner. There's no debate about who's the winner. So when you have data that looks like that, you can afford to train in high dimensions. Like in a chess game, the number of permutations of chess moves is astronomical. But with having infinite signal to noise ratio, you can learn how to win at chess. Teach a machine to do that. So you may get an uninterpretable result, and you may not be able to separate the predictors, and you don't actually get formal interaction effects, which are like double differences. And then you have if you don't have something like a game with a infinite signal to noise ratio, your sample size the requirement is very high. And so something really odd has happened in the last 10 years is everybody was talking about big data. And to some extent, machine learning created the need for big data. There's a lot of situations where if you were not using machine learning, you would need small to moderate data. But some sample size estimates for using machine learning are things like this: 200 events per candidate predictor when the outcome is binary, whereas logistic regression may require 20 events per candidate variable. So you need 10 times the size of the data set. And that's because you're allowing interactions to be chosen with the same priority as main effects. In other words, you're not favoring additivity. So this was an interesting article that said one company adopted machine learning, and they spent all their time tuning the machine, and they weren't paying any attention to the data quality, and they were putting a lot of garbage into their analysis because of the need to tune all the machine learning algorithms. They ended up dropping all machine learning and using logistic regression for everything, simplifying and spending their efforts getting the data clean, and they actually were better off. All right, so we have some standard notation for regression models. We have predictors. We have regression coefficients. We may have an intercept. Some models have more than one intercept. And then we have what's called the linear predictor, or X beta. So this is just our weighted linear combination of the X's. And there's an understood column of X's that's a 1. So you can multiply 1 by beta 0 and get beta 0. So this is called the linear predictor, and it's at the heart of regression models. And a regression model is some sort of connection between X and Y. And I write it this way because it can be more general than things like means or probabilities, because you might be doing quantile regression. And so you might be modeling the 25th percentile of height given age, say a growth chart for a pediatrician. So we tend to model expected values a lot, long-term average or expected value, mean. We tend to do a lot of binary logistic regression, but this notation is much more general than that. You can model hazard rates, quantiles. You could model the interquartile range. You could model the variance or the log of the variance. And so we form general linear regression models look like this, and this covers a lot of different models, including the ordinary linear model, where you're modeling the property of the response is the expectation. We might be assuming normality condition on X. So given X, Y is normal, which means your residuals are normal. And we often linearize the model, and we do that just to make the regression coefficients easier to interpret. It doesn't really help in many other ways. So if you had a logistic model, the inverse transformation of that is the logit transformation, this. And so we might state the model in terms of the logit, because then we can interpret the betas as differences on the logit or log odds scale. So that leads to helping us interpret the parameters. So you can go through and just see what things cancel out. So if X sub j was linear and did not interact with anything, raising X sub j by 1 unit compared to leaving it where it was is going to increase C prime by beta j units. So that might be an increase in the log odds, might be an increase in the log hazard, might be an increase in the median if you're doing quantile regression. Then you just need a way to handle different predictors. So we're not going to really spend much time on that, but this is just standard indicator variable notation. And then interactions might be as simple as adding a product to the model, or it might be nonlinear interaction. And at your leisure, go through this in detail because it just helps you nail down that you can interpret the regression coefficients in the presence of a simple interaction between two variables. Now, one of the things that's very important is what's called a chunk test or a composite test. So a chunk test is just a test of more than one parameter at a time. And you can do a chunk test by leaving the parameters out of the model and looking at how much the model falls apart, like how much did the R-squared drop. Or you can do it with a single big model using things like wall tests and other kinds of tests to test combined effects of multiple variables. The reason chunk tests are so important is when you get into nonlinear effects and interactions. So in this particular model, we have an age by sex interaction, and we can do a chunk test that asks whether age is associated with the outcome. So when you have a model like the one we had up here, this is the statement of the model. Age appears in two ways. It appears as a main effect, so-called main effect, and it appears as an interaction effect with sex. So if we want to ask whether age is associated with an outcome, age has two opportunities to be associated with the outcome. And we need to make sure, this one and this one. So beta 1 and beta 3 are going to be tested jointly in a chunk test. And that is testing whether the relationship between age and Y is flat or not. So you could say you're testing whether there's an age main effect or an age by sex interaction, either one, which is equivalent to saying, is there a relationship between age and Y for males, or is there a relationship between age and Y for females? So this is a chunk test with 2 degrees of freedom, and that is going to give you a much more meaningful test than just looking at the beta 1 coefficient, because that's going to be the age effect only if you're in the reference category for sex. Whereas the chunk test is much more general, and it's much more free of how you coded the model. And then there's another kind of chunk test, like if you use R notation, Y is modeled as an additive model in age, sex, weight, waist, and tricep thickness. So these 3 variables may be collinear, and so we might want to get a chunk test that instead of trying to let them compete with each other, we're going to combine their effects into a 3 degree of freedom composite or chunk test. So in the RMS package, it would look like this. You would say, you would get your fit object, and then you would say ANOVA of fit, and you list all the variables that you want to combine. So if these were all linear, this would be 3 degrees of freedom. If these were not linear or they interacted, this would be more than 3 degrees of freedom, and it would all be automatically handled for you. So that's using matrix algebra to give you your 3 degree of freedom or more test. So that's a test of whether any of these is associated with the outcome. So chunk tests are really underused, and they're very helpful, especially if you have things like collinearity or interactions. Tim asked the question, would you say that a deep learning algorithm outperforms a regression model always if the number of observations is high enough and your only aim is making the correct predictions? I would not say that, but I would say if you have strong interactions in your data that were interactions you did not know to pre-specify in the regression model, then machine learning can very much outperform the statistical model. So it really depends on how non-additive things are. So when you need to have some kind of definition for machine learning. I've gotten into some really ugly arguments with people who say machine learning is everything, and then I tell them, well, if it's everything, it really means nothing to me. So I need a definition. So to me, the simplest definition is a statistical model is something that's predominantly additive, and a machine learning algorithm is something that's not predominantly additive. So this is where we get into handling continuous variables. And one of the things that people want to do is to avoid a linearity assumption by binning the variable. A lot of people try to do this with machine learning, and it's a bad idea in that context as well as in statistical models. And so relationships are seldom linear. Even when you're predicting a variable from itself, I'm finding a lot of nonlinear relationships. But if the way you handle nonlinearity is to categorize a variable, it really doesn't work well. It's a disaster from every standpoint. So we have a lot of references, and we have a key topic devoted to this on datamethods.org that has all these references in it and a lot more. So when you categorize variables, you get misleading answers, and you make other variables seem to be more important than they are because of residual confounding. So this is really not the way to handle nonlinearity. So the problems are legion, and when you categorize, you're assuming a flat relationship within an interval. So if you think about drawing the predictions, you'll have something, well, those are supposed to be two flat lines. You have a categorization such that when you cross a boundary, you're in the next bin or category. So you're assuming piecewise flat relationships when you categorize. And we just do not see piecewise flat relationships in almost any field of study. The only place you see it is when there's a law. So there's a law that you're not supposed to drive before a certain age. We see health insurance take a big leap at age 65 because people for the first time have a national health care policy. They have Medicare. And so when there's a legal mandate that's age-related, you're going to see a threshold effect. You're going to see a jump. But when it's not a legal mandate, we just don't see that. And so categorization assumes piecewise flat relationships, and that's really not going to cut it. When you make categories, because of sample size limitations, your outer categories have to be wider, and that means you're lumping unlikes. You're not distinguishing heterogeneous X's. So categorization assumes there's a discontinuity, and the only place we really see that is like a legal mandate that's age-related, or if there's an event. So whenever you have time as your variable, so if you have something going along, and then you can have an event happen because of somebody has a heart attack, or the CEO of a company is indicted and the stock price takes a big hit down. When this is time going across, you can have a discontinuity. But if X is not time, you're just almost never going to see anything like that. And when you categorize, the estimates are actually not even interpretable. And this goes into detail about that. Cut points that people claim to find, they never replicate because they don't exist in the first place. So for a cut point to exist, you have to have a discontinuity actually in the data. And since we don't find that, people don't replicate the cut points. So here's two examples from breast cancer field research where people have claimed to find different cut points on two different markers, and no two studies have been able to find the same cut points. So anytime you're searching for something that doesn't exist, you're going to find a different version of that thing that doesn't exist than somebody else finds. So it's really not surprising. Let's see if there's anything else we want to. This just lists the assumptions you make if you're using a cut point, and these are very tough assumptions that are just, I've never seen this really hold. Piecewise flatness. This is an interactive program you can run really easily. And when you run this, it lets you add noise to the data to ask the question, how much noise would you need to add to an X variable before fitting it as a continuous variable is worse than dichotomizing it. And what you find is there's no limit. So no matter how much noise you add to a variable, dichotomization is always worse. And that's because if you dichotomize something that's noisy, if you put it in the wrong side of the threshold of the discontinuity, that is a 100% relative error. So you might be making an error that's so big that you pay a big price for it. So here's a classic example from the medical literature of misleading results. So they're relating hemoglobin A1C, which is here, and it's this black line. This is a marker of diabetes, relating that to the probability that over a certain period of time, somebody will develop a very serious complication of diabetes, which is diabetic retinopathy. And so if you look hard at how this graph was created, this used really no statistical principles at all. And you see the intervals have varying widths. So you have a pretty wide interval here, then the intervals get smaller. And here you have an open-sided interval, 6.2 and above. And so they didn't label these correctly. They're labeled as if the intervals are equidistant. And then there's a mislabeling. When you're at 6.2 and above, that's an open-ended interval. So this might represent 6.2 to say 10. And the mean hemoglobin A1C in that interval might be, let's say, 8. So if you got a point like this one here, and it should be drawn where X is 8, that's way off the chart. That's going to be way out here. So when you connect to where it should have been drawn, you're going to get a much, much flatter relationship. So they made a big deal here about a threshold at 5.9 or 6.2, and the data don't support that in any way, shape, or form. This is really an optical illusion caused by bad statistical graphic. And so you need to, if you're using intervals, you should at least put the X's at the right location, which would be the mean of the hemoglobin A1Cs within the interval, but you really should not be using intervals. So we'll show an analysis that's a very good analysis shortly that has the same kind of data in it, where they use spline functions to estimate the relationship. So this idea that there's a threshold is something that influences medical practice a lot. And these thresholds have never been validated in any data set, but you'll hear physicians using these thresholds all the time. Just see if anybody had a new question here. I'm not sure I've mastered how to look for new questions. All right, don't see it. Okay, so I hope everybody understands this example.
There was a question about chunk tests.
Yeah, okay, what was that in the Q&A? Okay, let me see if I can find it.
It's in the chat. Maybe everybody ought to use the Q&A so you don't have to look both places.
Oh, okay, yeah, I'm not sure which one is best, to tell the truth. So do chunk tests, Carrie is asking, do chunk tests only work for predictive models, or they also have a role in causal inference? I think they have a role in every kind of analysis. It's harder to do causal inference if the chunk involves a mixture of types of variables. You know, a chunk could have a causal variable and a non-causal variable in it, and then the interpretation might be very difficult. But it's just very common. Like one of the places where causal inference has a lot of problems is when you have a non-dichotomous feature. And let's say you have spline terms, so your exposure variable has 4 degrees of freedom, has 4 parameters. And so you need a chunk test that's going to have 4 degrees of freedom. But to do standard causal inference on that might be a little tricky. Yeah, good questions. Please keep them up. Let's see. Oh, we had another question, say, from Macy. We have to think about many dimensions. We could talk about the number of rows, columns, or time points. Many algorithms of complexity is order of n squared with the number of columns and linear with the number of rows. That's why genomics data is problematic to work with, because we have so many columns. Yeah, couldn't agree more. And I've got this other set of notes called Biostatistics and Biomedical Research, BBR, and it has a chapter related to that with the challenges of high dimensional data analysis. So when we get to, let's see if anybody added anything in the Q&A. Oh, what is the hypothesis behind grouping variables in the chunk? So the chunk is going to be created because of subject matter expertise, or it's going to be created because of collinearity. So when things are collinear, you can't really estimate the effect of one without changing the others. So the chunk test is going to keep you from allowing collinearity to be a problem. So sometimes chunk tests are built on observed collinearities, like looking at the correlation matrix. In other cases, the elements of the chunk are pre-specified because of some special meaning. Another good question. So when we get back to modeling, this is our first line of defense against the linearity assumption, is to add a quadratic effect. So now we got like age and age squared, and that's a very standard thing that people are taught to do in their first regression course. And it's really a lot better than just assuming it's linear, but things really are not that simple. And this is a symmetric function. So this will have a vertex, and then the relationship between x1 and y will be symmetric around that vertex. So that's going to be too restrictive, and it won't always give you accurate predictions. But you can't just keep adding higher powers, because if you add a cube and a fourth degree term, you're going to create a wiggly kind of thing that doesn't make sense, and it won't allow any sort of threshold or logarithmic type of shape. And so that's what gets us into piecewise polynomials. And the first one that we're talking about is a linear spline function, but a spline is something that is flexible, that you can bend, so that when you're trying to draw something and you're trying to create a smooth connection, you can bend this strip a little bit and take your pen and go along that, and it keeps you from having an elbow in the corner. So that's what a physical spline looks like. And what we do with arithmetic is to use piecewise polynomial to do that. So a spline function is piecing together things, but we start with a piecewise linear. So we're gonna join linear relationships together, and these points here are called knots or join points. So given the join points, we're going to allow the slope to change, and then we'll quickly go back to the smooth case where we allow the curvature to change and not just the slope. So splines are very general purpose tools. So this starts off with a bilinear relationship, but we already need to get a little bit complex to force simple continuity. So we've got an initial straight line, and then we write it this way by multiplying by an indicator variable is x greater than the join point. Because when we subtract x minus a and we piece this together, this will be the initial slope. This will be the slope, the change in slope. So when you piece it together, you're going to get something like this, and you're not going to get something like this. So those curves don't meet. And so you have a zero order discontinuity. Now, Tim raises a very controversial point that I want to get to. Categorization is a good option to handle outliers in data sets. I don't see that because you're going to find you're grouping points together that are very heterogeneous. And so the way that I handle outliers in data sets is I'll make a transformation to make the X variable a little bit symmetric, and then I'll apply a spline to that. That's just to keep from the extreme values from being very influential. But when you spline, let's say you take the cube root of something that's highly heavy-tailed on the right, you take the spline function or a quadratic function in the cube root of the variable, you have the best of both worlds. So you're gonna not lose any information by grouping points together that are not the same, but you're not gonna allow outliers to be overly influential. So categorization, in my mind, still has a problem. Um, uh, it's not the way to solve an overly influential or point or outlier. So this is just showing you how to do piecewise linear, and this would be a piecewise linear that has 3 slope changes. So the plus notation just means, it just means if that term is negative, ignore it. So if x is less than b, pretend it's not there. So beta 3 is going to be a slope change as x crosses b. But the plus notation and the minus b is going to make these lines meet up without having a 0 order discontinuity. So this is what a linear spline with 3 knots looks like. Now, one of the things you'll notice about real world data is you don't have discontinuities in data unless there's a legal mandate sort of time effect, age effect. But we also don't have discontinuities in the slope. So this linear spline has discontinuous first derivative. We don't even see things in nature that look like this very often with an elbow. So we don't see sudden changes in the slope or first derivative. You can fit almost any shape with a linear spline, but we really don't like having these elbows in the graph. So that's going to make us move to a nonlinear spline, and this is what we tend to go to. We don't use quadratic splines very much because they don't allow as many continuity restrictions. With a cubic spline, you can have 3 levels of continuity, which you'll see in just a minute. So we start with a regular cubic polynomial, and you see this is what a regular cubic polynomial looks like. But then we're going to add I'm going to oversimplify this and call this a shape change at x equal to a, and another shape change at b, and another shape change at c. It's not exactly a shape change, but it's something very specific we'll get to. But by allowing the curve to change shape and acceleration at a, b, or c, you're actually piecing together things. That's not supposed to have a gap in it. You're piecing together things where you can't see these gaps. But the way you're piecing together the curve is so flexible that it will handle a huge number of situations. Now, there's a big picture to this to start to understand, which is we're adding more parameters to the model. If you have an important variable, it's going to be worth adding a lot of parameters for that, because if you don't and you underfit the variable, you may make other variables seem more important than they really are. So another way to say that is if you don't assume something's linear, the boost that you get in your R squared may be such that it's like discovering a new variable that nobody ever knew about and adding that to the model. So in other words, if you allowed age to be nonlinear in a flexible way, that might bring in the information that some new expensive biomarker was going to bring in. And you don't need the biomarker at all. You just need to model age better. So what is happening with a cubic spline? If you write out this R code and you evaluate this spline function that is right here, so y is calculated there. You see that's a cubic spline function, and the coefficients b1 to b6 are given above. And then y1 is the slope, so it's the first derivative. y2 is the acceleration or second derivative, and y3 is the jolt or jerk, which is the third derivative. So why do we care about all that? Oops, we care about that because it helps you see what's underneath the hood. So this is the function that we're trying to approximate. So with a spline, we can fit almost any shape of function as long as it's fairly continuous. And then if you looked beneath that and calculated the slope of the curve on the top, you get the first derivative, which is the rate of change of the function in the top. And so you see that over here in the left tail, so this is a very slow rate of change. So that means the slope is close to 0. Then you see a faster rate of change. The slope is creeping up here. Now, if you go back to the third line, that is the rate of change of the slope. So that's the acceleration. So you see the slope of the slope, which is the acceleration of the top curve, is a piecewise linear spline. And then we don't get categorization until we get to the jolt or jerk, which is the third derivative, which is the rate of change of acceleration. So what you could say is a cubic spline function is a way to categorize the third derivative of the function. So we're not categorizing the function at all. We're categorizing the third derivative into piecewise flat intervals with a sudden change in the third derivative at the knots or join points. So that's what's actually happening when you add a knot. You're allowing the third derivative to suddenly change. But since the human eye cannot really look at a graph and see a change in a third derivative, you look at this curve on the top, you see nothing but smoothness. So this is the way you can build smooth fits that are flexible by only dichotomizing at the third derivative level. So that's sort of what's under the hood of a spline function. We're going to go one step further, because when you look at a spline function like this, let's look at it in general terms up here, that has a lot of coefficients, and it still may have a little bit of a problem with wiggles, especially at the extremes. And so the way we're going to put a restriction on this, we're going to have 4 fewer parameters, and we're going to allow for less wiggles in the tails by making the function be linear on the left and linear on the right. So when you're making a function linear on the left, that's this first thing that I circled. That's over here. So to make this function linear, beta 2 and beta 3 have to go to 0. So we're just going to get those out of the model. So now our function is going to be linear when x is less than a. A is the first knot. Now to make the equation linear when x is greater than c, the arithmetic's a little messier, but it's not that bad. But the easiest way to do it is to set the third derivative, set the second derivative to 0, and that is the way to force the equation to be linear. And then you can solve for what restrictions you have on beta 5 and beta 6 that make that happen. And when you work through that little bit of a mess, the restrictions are listed over here. So we're going to form new terms that have differences now. So xj plus 1 has cubes and differences in cubes weighted by differences in the knots. And by doing that, these terms now are such that when you look at this equation up here, this equation is linear in x when x is less than the first knot t sub 1. And then all of these terms are linear when x is greater than or equal to the last knot. So you can evaluate any of these terms, xj plus 1, and you'll find that beyond the outer knot, they're all linear in x. So any combination of them is going to be linear in x. So that's how we put the linear tail restriction on the right, is we have these derived variables that are differences in these spline terms weighted by knots. And those are the ones we actually put into the fitting process in our model. This is called the truncated power basis for splines, and these are also called natural splines. So these are basis functions that you're creating. And so we're finding linear combinations of these basis functions here. So you start off with a positive coefficient of this, that means your curve is rising. And then you have a strong negative coefficient of this, that means your curve is going to start to rise, and then it's going to take a downward turn. So these are called basis functions, and you're finding the coefficients that you multiply by the basis function, and that gives you your fitted curve in that predictor. So that's what restricted cubic splines are really about. And this just shows you a random collection of fitted cubic splines, restricted cubic splines. And you can see when there's 3 knots, these look like quadratics because the 3 knots were equally spaced. And then in the upper right, you have more variety. Then you get to 5 knots, more variety, and 6 knots, you keep getting more variety of the fits. So the variety of fits that you'll allow will go up as the number of knots goes up. And you can really fit almost anything you can throw at it unless there's a discontinuity. And in that case, you would have to have 2 knots that are very, very close to each other to handle a discontinuity. All right, see if anybody had any questions about spline functions.
There's a question about placement of the knots.
Yes, we'll get to that. We have totally avoided that topic, and we're about to get to it. So when we're done, we're going to re-express the function like this, because that's in the simplest form, and that's by writing beta k and beta k plus 1, which are redundant with the earlier betas. So we have 2 betas that are linear combinations of the earlier betas because of the linear restriction on the right. But we can write it in unrestricted form. And so there's a function in the RMS package that will write out the math for this, for your fitted model, and it's writing it out using this form you see here. And we can easily get chunk tests. And so we'll see this more in case studies. And we'll also see what makes all of this work when you're in R is that R allows a predictor variable in any model to be a matrix. So a spline function is nothing more than an n by p matrix, n observations by p parameters, and you're adding matrix columns using these terms like you see here, but with the differences in cubes. And by the fact that R allows any predictor to be a matrix means you automatically can handle splines, just like you handle regular polynomials are also matrices. So what's at the heart of the R regression formula language is what makes splines so easy to deal with. So here's some examples where they analyzed hemoglobin A1C the right way. They did it as a linear spline and as a restricted cubic spline. And the linear spline has elbows in it that I don't really believe. So I like the restricted cubic spline better. So you see when you're relating hemoglobin A1C to adjusted hazard ratio for getting diabetes in the future, it's a almost linear kind of relationship. Of course, it's a log scale on the y-axis. When you ask what's the prediction relationship between hemoglobin A1C and the risk of coronary heart disease, it's a hockey stick relationship. If you put a threshold and you categorized hemoglobin A1C, you would totally miss this. So you see it's not good to have a very low value. And then once you get above 5.5, the risk increases, but it increases almost like a straight line. So there's no such thing as a discontinuity or a threshold. And then if you look at the risk of stroke, it's very smooth, and the risk of all-cause mortality is very, very non-monotonic. So you can see that a threshold analysis is going to try to call these people all the same, and it's going to try to call these people all the same. It's going to miss that it's bad to be very low or it's bad to be very high, and it depends on how high and how low you are. There's nothing remotely looking like a threshold analysis like that. So I think this is a very, very reasonable analysis. So then you get into this question somebody's also already raised, is how do you pick the number of knots? Well, these functions are so smooth that it doesn't matter very much where you put the knots. They have so many restrictions on them. that the flexibility comes more from how many knots you have. You can change the fit a little bit by changing the knot placement, but it'll change it less than you think. So what's really important is to put the knots either where your subject matter knowledge says there's a jolt in the relationship, or you put the knots where you can afford to put knots, and that's according to your sample size in different intervals. So we're going to pick quantiles of the predictor as our default knots if we don't have any subject matter knowledge. So if we have 3 knots, we're going to put the outer knots are going to have 80% of the data between them. And between the first and second knot is going to be 40% of the data. Also between the second and third knot is 40% of the data. When you have 4 knots, we're going to go from the 5th to the 95th percentile of X, like age. And between any 2 knots is going to be 30% of our data. So without any subject matter knowledge, we're going to put knots where we can afford to put them, which is according to the sample size. And the quantile is what keeps the sample size in mind. Once you get out to 7 knots, you would only do that for a large sample size. And once you get to a large sample size, you can afford to look way out in the tails. So you can get out to the 2.5th and 97.5th percentiles to look at tail behavior when you have a large sample size, which is what you would need to fit 7 knots. So those are the default knot placements. If you had a relationship, let's say it was going along like this, and you knew from the subject matter that it let's say I didn't even draw that accelerating fast enough. If something accelerates super fast and you didn't have a knot in this region, you would miss that and you would sort of cut that off and make that more linear. So if you knew something had a super fast acceleration at a certain point, you would want to make sure you have a knot there, which would take some outside knowledge because these are pre-specified knots. So the choice of the number of knots is critical. We're going to have a little bit of help for that. But it's going to depend on 2 things you have to know. It's going to depend on your sample size. So what's your information available? And then it's going to depend on how many other variables need knots. So if you couldn't have 20 variables and give them all 5 knots. It's going to be a lot of parameters. So the number of variables that may not be linear, but they are continuous, that's going to change how you assign knots to any one variable. So we need to have a strategy that helps us with that, and we will be covering that. All right. So knots, restricted cubic splines and knot choices are big things to get into. What you're going to find is the reason we spend so much time with splines is they have lots of advantages. They give you an equation. You can use any software to fit a spline in any context, and they're using standard maximum likelihood or least squares or penalized regression. So it works in the context that we already know and love. And then you can estimate transformations using splines. If you use a non-parametric method, you don't get a prediction equation. I sort of like having an equation. It makes prediction easier. And you can extend it to non-additive models so you can have interactions between spline functions. So that is a crash course on splines. And we're going to see in a case study what we're going to do with all that. This is a section, just a rehash of some stuff about machine learning and how to choose machine learning versus statistical models. So the nice thing about machine learning is if you think interactions might be very important, but you don't know which things interact, things like neural networks can deal with that. And also if things are very nonlinear, they can deal with that also. But you need such big sample sizes for neural networks and for other machine learning methods such as random forest that it's a real challenge. So if your signal to noise ratio is wonderful, your effective sample size is much higher. So let's say your true R squared was 0.9. You don't know it's 0.9, but let's say it really is 0.9. That's a high signal to noise ratio, and you can get away with modeling a lot of complexity when you have such a high signal to noise ratio. So machine learning could work very well, which is why if you're doing visual pattern recognition, machine learning works so well. The signal to noise ratio in visual pattern recognition is extremely high. Even though it may be a difficult problem, the signal is much higher than if you're asking about customer behavior or what's the risk of ovarian cancer or something like that. So that helps you know why certain situations tend to work better with machine learning, but it assumes that your effective sample size is very large or your signal to noise ratio is very, very large. All right, let's see if there were any other questions that we've been missing. Okay. Oh yeah, David's asking a good one. Do you generally expand all continuous predictors into splines as a matter of fact before fitting the first model? We do that in a certain narrow sense. So we're going to have a strategy to deal with that. So if you just hold that question. There are cases where the sample size is so big, we just say, okay, let's let every variable have 4 or 5 knots. But in the more general case, the sample size doesn't allow that, and we need a strategy to give priority to certain variables. So we're going to cover that briefly coming up. Okay, so let's see, where do we cover that? This is a section on interactions that gets to be pretty challenging, but you can have products between nonlinear terms to fit general interactions and plot those as smooth surfaces. So here's an example. So interaction between two regular splines is a tensor spline, and this is kind of a heat map where the hotness of the color is proportional to the predicted risk of a stroke. So here we have diastolic blood pressure on the x-axis, systolic blood pressure on the y-axis, and the heat spectrum is telling you how high the risk of a stroke is. So you can see the dominant factor there is as you go at the 45-degree line, which is mean arterial blood pressure, your risk of a stroke goes up. And once you get to a high mean pressure, the perpendicular line starts to have a little bit of information about risk, which is called pulse pressure, the difference between systolic and diastolic blood pressure. So that's one way you can represent an interaction between two continuous variables if your sample size is reasonably large. There's a lot of material we're not going to cover that you'll want to come back to, and this is one of the more important ones where you start to pre-specify interactions based on your understanding of the subject matter. To me, this is one of the most important things to do. I've never found a case where searching for interactions actually is a stable process that replicates or validates. So I don't find interactions as something good for exploration. It's something good to think about and pre-specify to the maximum extent possible. And that's just because there's so many possible interactions you need to prioritize. So this shows you in a medical setting what is a way to prioritize the interactions according to which interactions we find are actually important in real data. So you need to create your own version of this for your data sets so that you know how to prioritize interactions and pre-specify them in your model. So here's an example of something that could be a very important interaction. So it may be that you ask somebody, how often do they feel pain in a given day? And then what is the typical severity of the pain? It may be the way that predicts some outcome is to multiply the frequency by the severity. So that's a form of interaction. All right. This is a little bit of a diversion that just shows how to use the RMS package to go beyond splines and how you can have more complex relationships. This is really necessary when you have things like time trends, like seasonality. And so I'm just going to highlight a couple of things. So this is a spline fit. This happens to be in a Poisson model for disease case counts. And we're going to have a restricted cubic spline in time with 6 knots chosen at default quantiles. So RCS is a function in the RMS package that creates a matrix. And that matrix is going to be used as predictors in your regression, just like they were separate variables. But they're going to be kept together for when you get chunk tests or predictions. So this is what a fitted spline function looks like in calendar time. But then we can do something like have our spline, which we're going to have to use this function so we can take control of where the knots are placed. And then we're going to add a harmonic function here. We're going to add a sine and cosine with a period of 12 months. So this is how you specify seasonal trend that has a period of 12 months where you don't know where the peak of the trend is. So by having both a sine and a cosine term in there, you're estimating beta coefficients for the sine and the cosine. And so that's going to be your seasonal trend. And then the spline in time is going to be your long-term trend that goes past multiple years. So this just shows how easy it is to have a long-term trend and seasonal trend in the same model. And then when you plot that, you see that you have your long-term trend over 60 months, but then you have a yearly seasonal trend, and you can solve for this when the low point and the high point of the trend are in terms of what month of the year that is. And you can also add more knots so that you might have a sudden change if there's a part where you think they might be a sudden change. And you can also add a true discontinuity. So this is what a true discontinuity looks like. This would be like an interrupted time series analysis. So we're going to add a variable that is the discontinuous variable called jump. So when you're greater than or equal to 37 months out from the start of the study, this is going to be a binary variable that's added to the seasonal trend, which is added to the long-term trend, such that when you plot that, you see that I say it's predict. That's in the RMS package. That just makes predictions real easy to get. And I'm going to pass that into a ggplot method so that when I plot that, I get my prediction and my confidence bands. And you can see I'm allowing for a complete discontinuity, a zero order discontinuity doing it this way. So you can take this spline idea and also categorical variables and combine all this to allow any sort of exotic fit that you think is appropriate for your situation. All right, so in just a few minutes, we're going to take a very short break. This is one of those chapters that's super important that we don't have any time for today, and that's the missing data chapter. What we're going to spend a fair amount of time on is more the strategy chapter, where you start putting things together, and we'll talk more about how many knots to place and so on. Oops, someday I'll get to it. So this is where we get into what to me is the real fun stuff, which is our strategy. So spending degrees of freedom is something you have to understand to have a good strategy, in my view. So spending degrees of freedom means examining or fitting parameters in a model using supervised learning. So in other words, you're using the outcome data in what you're doing. So that means you're actually fitting parameters, you're looking at scatter plots, you're examining tables that include the outcome variable. So anything that uses the outcome to tell you how to model is actually effectively estimating parameters or spending degrees of freedom. And if you want to have the right standard errors and confidence intervals and not have overconfidence, you can't retrieve parameters once they're spent. So if you fit a nonlinear trend and you decide that the nonlinear trend wasn't worth it, and you go back to a linear trend, your standard errors will be wrong. They'll be too small, and your confidence coverage will not be correct. So you might say it's 95% confidence interval, might be an 88% confidence interval, really. So if you look at a scatter plot and that suggests linearity, it's really hard to know how many parameters you've spent, but you spent more than one parameter to look at that scatter plot if it alters how you model. So our strategy is to decide how many parameters can be estimated. You don't have to estimate that many, but you probably should not estimate more than that. And then you decide where in the model the parameters should be put. And then you estimate the parameters and don't feel bad about it. So you're going to estimate or spend degrees of freedom and not try to retrieve them if their p-values are large. So the idea of excluding variables because p-values are large is one of the worst ideas that's crept into statistics, and this really has affected epidemiology to a huge degree, unfortunately. So there's a lot of choices you have to make, and this is one of the things that helps us allocate the degrees of freedom. So the idea here, this is going to be new to most people. The idea here is that you're going to give more knots to variables that have more promise. And so how do we know that something has more promise? Well, it could be known from previous research. That's the best thing to do. Or it could be known by observing something in the data if you're careful. So this is going to be a section about how to be careful when you're going to assign a certain priority to a certain variable, such that if the variable has more potential, it's going to have more opportunities to be strong and to be flexible in your model. So that is the idea at this point. So these graphs are going to give you the background understanding of what we're talking about. So if you had a relationship that was really flat and you fitted it as a nonlinear relationship, you'll get what the blue curve looks like. And so that's going to be a very non-fatal problem. You are overfitting a flat relationship in the top left graph. And that one can be solved. We could make a weak variable be modeled as linear. And then the linear would not have those waves in it. What's on the upper right is having a very strong relationship that's linear, and then we're overfitting it. So we have a strong linear relationship that we allowed to be nonlinear. So we're going to have some waves in that fit, and those waves are going to be unnecessary, but we don't know that. We don't have enough knowledge about the subject matter to really know that. So we're going to risk making this error, and we're going to be not feeling bad about it at all. So we're going to allow a steep relationship to be over modeled. And what we don't want to do is to make the opposite error. And so this would be a really serious error. So you see that we have 2 points where we're right, because the straight line that we fitted, we're underfitting the relationship. It's really curved. We're making it linear. We are underfitting it. We're right in only 2 points, but we have a pretty bad error here and a bad error here and here. So that is underfitting a steep relationship that is not linear. That's a mistake we want to avoid. And then the worst thing you can do is having a monotonic fit to a strong non-monotonic relationship. So non-monotonic, it goes up and then it goes back down, starting here. So by underfitting that, we have a flat relationship that is horribly wrong. So we have a huge prediction error here. We have huge prediction errors there and there. So that is underfitting a complex relationship by forcing it to be linear, and it came out being flat. And we totally missed the fact that the association between X and Y is really strong. So avoid making a tragic error, avoid making a serious error. Allow yourself to make an error that's not serious, mainly this one up here in the top right. So that's going to be what's driving our strategy about not giving the same number of knots to the different variables. So let's take about a 5-minute or so break and together a little bit after 10 before the hour. And I'll try to catch up on some questions during that time. And I'll see you back in just a little over 5 minutes. As we reconvene, I want to mention there's some great comments in the chat and Q&A, including some useful links. And there was an issue raised about Occam's razor by Mychek. And I just want to mention a comment about that, because Occam's razor is commonly invoked in this setting, but it doesn't actually apply in my mind. So Occam's razor would be if you had two pre-specified explanations for something, you would favor the simpler explanation. So let's say somebody thought something was linear and somebody else thought it was a cubic polynomial with 3 parameters. And if they performed roughly the same, you might favor the linear one. But Occam's razor doesn't apply to things that are not pre-specified. So, and just in general, things are a lot more complex than we tend to think they are in human activities, plus maybe even non-human things. So you wouldn't say that you favor something that's simpler if you had to work at finding it to be simpler. In other words, if the simple thing was not pre-specified, but it looked like it was performing okay compared to the complex thing, but the simple thing was determined after massaging the data a lot to reduce parameters, then Occam's razor would not apply in that situation. So I think you have to be careful what is the context for Occam's razor. It doesn't apply to sort of post-data massage. It applies to like 2 pre-specified explanations. So what we were talking about was a strategy to not give every variable the same complexity. And there's two strategies in the notes for doing that. We're just going to go through one of them, and that is learning from a saturated model. So the idea is you fit a big model, and then you look at it in a semi-supervised way. So the emphasis here is this is not unsupervised learning. So this is not principal components analysis. This is not supervised learning where you look at all the coefficients, but this is semi-supervised learning. So what in the world does that mean? So what that means is, let's just look at some code. So this says in the RMS package, fit a logistic regression model to predict Y. Y could be ordinal or binary. And we're going to have main effect for sex. Race might have 10 levels. Restricted cubic spline and age with 5 default knots based on quantiles. Same for weight, height, and blood pressure. So we're allowing the maximum number of knots that we think we would use in this problem. And we're not grouping any of the races. Of course, sex may only be 2 levels, so it's not much you can do there. And then we say, if we set ANOVA, what we would get there would be all the possible chunk tests from this model. So one of the chunk tests would be how much nonlinearity is there for blood pressure. So that would be something that would give us fully supervised learning. So we don't allow ourselves to see that. So we don't print the ANOVA, we just plot the ANOVA. So what is a plot of an ANOVA does is a dot chart where we get the total effect of each variable. So if you get a chi-square for this variable and the chi-square is 0, so with 5 knots, you're going to have 3 nonlinear terms and 1 linear terms. You have 4 parameters. So you're going to get a chi-square with 4 degrees of freedom for this variable. If that chi-square is 0, that is a low potential variable. 0 is the lowest you can get. But we've already pre-specified that it's in the model. So it's going to stay in the model no matter if the chi-square is 0, the p-value is 1, blood pressure has to stay in the model. Otherwise, we are doing double dipping. And so what we're going to learn, though, is that blood pressure is not worth devoting a lot of knots to, and we're going to force it to be linear. So if that chi-square came out 0, we're going to force it to be linear. if this chi-square with 4 degrees of freedom came out as a 7, it's got some promise, but not great. We might give it the minimum number of knots at 3. So that's going to make it have 2 degrees of freedom. So things that have no potential, we're going to just force them to be linear. And things that have high potential, like let's say this chi-square was 100, we're going to leave it with 5 knots. So the reason this is a strategy that's semi-supervised and not dangerous is by not printing the ANOVA, we do not reveal how much nonlinearity is here. So when you look at this variable, the nonlinearity with 3 degrees of freedom might be 0. So this has totally a linear effect and no nonlinear effect. If we knew that, we might force this to be linear. So that would be double dipping. So we're not revealing the shape of the relationship in anything we're about to do. We're only revealing how steep the relationship is in a general sense with a chunk test. So we're using a chunk test to rank order the potential importance of variables so that the ones that seem to be not very important are going to be forced to be linear. And I've got some simulations that study the performance of this method, and it seems to be slightly conservative as a method, which is the direction you would want it to be. So that is one of our 2 strategies for ranking the variables according to their potential. But by promising to have a pre-specified model and never deleting a variable, the fewest degrees of freedom we're going to allow it to have is going to be 1 degree of freedom. So that is our strategy for not giving all the variables the same number of knots. There's a second way to do it I'm not going to cover today. All right. Let's see if any outstanding questions. Okay. Somebody, if there's a question somebody thinks I need to see that I'm missing, please somebody shout it out. Madeline has been good about that, I think. And Madeline, it's good to have you here. So this leads into one of the dicier subjects.
Thanks, Frank.
Yeah, good to have you. One of the dicier subjects, as Madeline has heard me talk about more than once, is variable selection. And this has been one of the great misunderstandings of statistics. And this is where the software got ahead of statistical common sense, because people implemented stepwise variable selection methods starting in 1964 with the old BMD system out of UCLA, BNDP. And no one was able to simulate the performance of variable selection until 1984, and we found it was horrendously bad. But it had already been implemented in all the software packages of the day, and so people are not willing to unimplement it, but it would not stand peer review if it came up again, if it was rediscovered. So what happens when you're doing stepwise variable selection is you're biasing everything you do because you're double dipping in one of the worst possible ways. And the p-values are not even accurate because the p-values after the first step in a backward step down, the F and chi-square statistics don't apply anymore. So we're not even using the right distributions to calculate the p-values. And basically everything that can go wrong will go wrong. So the worst thing about stepwise regression is it fails at what it's supposed to be best at, which is finding the right variables. It just has no chance or very limited chance of finding the right variables. So it'll find noise variables and call them important. It will call important variables noise and it omit them. And so the best thing to do is to just show a little simulation. So this is where the signal to noise ratio is high. You have a continuous outcome, linear model, everything's linear. You have only 8 candidate variables, 4 of them are truly related to the outcome. And we're going to select the best model using all possible subsets regression to maximize the adjusted R squared. And so what does that mean? We're going to simulate data this is going to simulate unrelated predictors. These predictors are all having a normal distribution. They're totally not collinear in any way. That's the easiest case you could ever have, and the method still is a total disaster. If you allow collinearities in the data using this, things just get worse. But we'll just look at the independent case right now. So we're going to create, these are the true coefficients. X1 is important, X2 is equally important, X3 is half as important, X7 is a little less than half as important. That's the true linear predictor. We're going to generate Y variables by adding the random noise to the linear predictor. And then we're going to go through our all possible subsets to pick a model, and we're going to see how it performs over simulations. So you can modify that code to simulate this in different ways. So we're asking the question, how often did stepwise regression find the right model in a simple case, no collinearity, high signal to noise ratio? And then how well did it estimate sigma squared? So here's a case where we do 100 simulations and the sample size is 20. And in 100 simulations, the correct 4 variables were found in only 2 out of the 100 simulations. So the probability that the stepwise model is the correct model was 0.02. The sample size 40, only 4 out of 100 stepwise regressions, when you repeat this with simulations, found the right 4 variables. When the sample size is 150, you're up to 1 out of 5. You have a 1 chance out of 5 of finding the right 4 variables. When the sample size is 300, you've got 1 out of 4 chance. You have to get to a sample size of 2,000, which is very large for a simple problem with a very high signal to noise ratio, continuous outcome. You know, if you had a binary outcome that's much, much worse than this, your probability of finding the right 4 variables with 2,000 observations that are noise-free, clean data is only like flipping a coin. So you can see a stepwise regression is just not doing what it's supposed to do. It just cannot find the right variables. And the moral of the story is the data do not have the information you need to find the right variables. The data do not have enough information to tell you which variables are important. And we're going to look at that in another way with confidence intervals. But does anybody have a question about this way of looking at it? That, to me, this is just about enough to scare anybody away from stepwise regression. I hope. All right, Madeline, maybe if you spot any questions I should get to, please tell me. All right, and we'll look at stepwise regression in one other way that I think is helpful and very practical also. So it just basically, everything can go wrong, will go wrong, and these articles are just wonderful. Stay away from step 1, 5 myths about variable selection, review and recommendations, stopping stepwise. These are all wonderful, and they're all very correct. And so basically the idea is you're trying to let the computer think for you, and it just fails pretty badly at this task. And this has a lot of ramifications because people are trying to claim they're discovering things in data, they're trying to develop predictions, and they're also using stepwise regression to adjust for variables, and they're not adjusting for the right variables. They're under adjusting, and that gives you residual confounding in your final analysis.
Questions?
Yes.
They're related. One is, what are alternatives to stepwise? You're going to get to this. And what about the lasso? One is from David and one is from Mariette.
Great, thanks, Madeline. Yeah, the lasso doesn't help at all. So I've got a separate simulation showing that the lasso cannot find the right variables in the simplest cases. So the lasso gives you false confidence about finding variables, and it has really terrible performance in terms of the probability of finding the correct variables. And then there was another part to the question, Madeline. What was that other?
Yeah, the other question is, what are the alternatives to stepwise?
Oh, yeah.
You've covered a little bit with looking at the ANOVA plot.
And to me, the
Yeah,
number
by
one,
not dropping them.
yeah, not dropping them. But to me, the number one alternative is data reduction or unsupervised learning. And so the beauty of data reduction is you're not asking something of the data that the data is not capable of doing. So at least not usually. So with data reduction, you're living within the confines of your sample size. Stepwise regression needs unbelievably large sample sizes to be reliable. Data reduction doesn't. So it allows you to live within your budget. And that is the greatest thing about data reduction. It's a method that can work for virtually every sample size, and it allows you to live within your means. So we're going to very, very quickly overview that, overview data reduction. So this gets into the roughest of all sample size formulas. This is very rough. This says that the number of parameters you can estimate, and that includes the number of candidate variables, if you're doing any stepwise. So it's not just the number of significant variables. The number of parameters should be less than the effective sample size over 15. Now that is such a rough rule of thumb, but it gets you started in the right direction. And so you have to be honest about what that means, because that includes nonlinear terms. It includes variables that you might later throw out. It includes interaction terms. And so it's derived from simulations by looking at how much of your data could you throw away before everything falls apart. Now, this is when the signal to noise ratio is not really high. So this is the kind of data that I have in the medical world and clinical trials, which usually is pretty noisy and hard to predict outcomes. In a high R squared, you can estimate many parameters. Now, somebody asked, I saw during the break, a great question about design of experiments, and this is a great time to bring that in. So when you have design of experiments, you have everything being orthogonal. So you might have a factorial design where all of the factors are completely uncorrelated with each other. That gives you tremendous advantages when you know there's zero collinearity in the factors. And the other thing about design of experiments is you tend to have a very high signal to noise ratio. So if you've ever looked at the design of experiments world, you'll see things like a 2 to the 5th factorial design where you would need a minimum of 32 observations to estimate 32 parameters. And you get by with 35 observations. You have 3 extra observations to estimate sigma squared. And then you have 32 parameters and 32 observations. That's how crazy you can get in a controlled experiment with a high signal to noise ratio. So this is a useful thing to think about when you contrast it with observational data, where you inherit all these crazy collinearities and a very poor signal to noise ratio. It is as different from design of experiments as night and day. So design of experiments is where you have total control. And that is a beautiful thing because you can have a lot of complexity. You can design, you could have a response service model that has all two-way interactions in it and still have it reliable. So these are the papers to really look at for sample size calculations for model reliability. I was a co-author on these, and this has a much refined way to calculate the sample size you need for the model to be reliable. And he has an R package to help you in doing the calculation. This is another way to look at it. If you wanted to estimate the residual standard deviation in a linear model to within a multiplicative margin of error of 1.2 with 95% confidence, that requires 70 independent subjects. So 70 is kind of a minimum sample size for regression, because estimating the residual standard deviation is key in linear regression. And this is what it takes to estimate this to be within a factor of 1.2 of the truth with some kind of decent probability. But getting back to our effective sample size, what is the effective sample size? If you have a continuous variable, it's going to be your number of independent observations. So that is your highest information variable you can have. This is your lowest information variable. And the lowest of the low would be a binary variable that's highly imbalanced. So the minimum of the number of events and the number of non-events would be what your effective sample size is close to in a binary outcome. So that is really going to hurt you. So if you have 100 disease and 100,000 non-disease, your limiting sample size is about 100. That's only one bit of information in a binary outcome. That's the worst you can have, other than have everybody have no disease. Because if you have no events, you have no information for modeling at all. So that's the worst of the worst. An ordinal outcome has this effective sample size. And so this is basically telling you, if you have k distinct levels, how small can you make the frequencies of those levels? In other words, how can you make this variable look like a continuous variable with no ties in it? So the fewer ties you have in an ordinal variable, the more it's like a continuous variable. And this tells you how to calculate the limiting sample size if you have an ordinal response. And you'll see if you have at least 5 levels and they're decently well populated, this will be very high efficiency, almost equal to a continuous. And then with a failure time variable, the effective sample size may be as bad as the number of failures. So the number of non-events doesn't contribute. If the censored observations in a Cox model do not contribute to the variance, they contribute to the point estimate, like hazard ratio. They don't contribute to the variance of the log hazard ratio. So your limiting sample size is the number of events. So this is what helps you plan your modeling so that you know how many degrees of freedom you have to work with. You should immediately be thinking, if you've ever looked at genetics, there's genetic studies with 5 million candidate variables and 300 patients that claim to discover the genes that are related to a phenotype. And then you ask yourself, based on all of this, is that mathematically possible to do that? And the answer is no, it's not mathematically possible because the chance that you're missing important genes is extremely high. And so, but it does get a lot of people promoted and a lot of papers in the medical literature. So in genetics, it's very common for the number of candidate features to be larger than the sample size. And the hope for getting useful results from that is pretty low. Univariable screening is in no way solves any of this problem. So shrinkage is something that's a general tool that we certainly won't have time to cover here, but it's something that's very important to look farther into. We're going to quickly look at data reduction. So this to me is my go-to method that works in just a huge variety of situations. So data reduction means you're reducing the dimensionality in the predictor space. So the number of parameters on the right-hand side of the model are going to be reduced before you ever expose the predictors to the outcome variable. So data reduction is unsupervised learning. It doesn't make use of the Y variable. And of course, one of the best ways to use unsupervised learning is to use previous research. We might be eliminating variables that have a very narrow distribution. We might eliminate variables that are just missing too often. But very commonly, we're going to use a data reduction method. So principal components regression is one of the go-to methods. And the thing that I'd like to see a good paper written on this because it's such an important point that we don't talk about enough. Principal components can be very unstable, and you may find that they don't replicate as you go from 50 customers in one data set to 100 customers in another data set. And so it's not that principal components is a magic stable thing and you can estimate all these coefficients and they never change. It's just that the way that they're unstable is not something that works against you or in your favor with regard to predicting the Y variable. So in other words, if your collinearities change, your principal components would change as you go from one sample to another. But the way the principal components change is not correlated with your performance in predicting the Y variable. So it's kind of, they can be noisy, but they're not noisy in a way that systematically is to your advantage. So if something like systematically to your advantage would be selecting variables according to p-values to maximize R squared. So that is drastically to your advantage. And that's why it's such a poor technique. It's biased. It's biased in your favor. So when you use data reduction, it's not biased in your favor. And it handles collinearities in a very nice way. So incomplete, it's called incomplete principal components regression because you might have 20 candidate variables, but you're not going to put 20 principal components into your model. That wouldn't accomplish anything. You might put only 4 principal components. So the 4 combinations of the 20 variables that explain the most variation in the 20 would be the first 4 principal components. You can improve a little bit with nonlinear principal components. And then there's things like sliced inverse regression, variable clustering, ordinary cluster analysis. Those are all unsupervised learning methods. So we might have a data set that has only 40 events and 60 candidate predictors. We can't really fit 60 variables against 40 events. That wouldn't even converge. It'd be a singular problem. You have a singularity in the matrix. But we can use some prior knowledge and we can create clusters for variables that we don't know to be very strong. So we're separating some variables out and we're clustering the rest and we're summarizing each cluster with its first principal component. So that's a method that I use a lot. So that's variable clustering followed by principal components. And the general way to do this is with sparse principal components. So it combines those 2 steps. And in the RMS book, one of the chapters has a case study of sparse principal components. And I was very satisfied with how that worked. So for the future, just make note that sparse principal components, and there's at least 2 R packages that do that, is one of the most promising techniques. So they're using the lasso in a place where I think it's really good to use the lasso. So they're using a lasso penalty on the loadings of the principal component to force a lot of the loadings to be 0. So when you move from the first principal component to the second, they'll have different variables getting non-zero coefficients. So it's really forming variable clusters as you move from one component to the next. And then the lasso part makes a lot of the coefficients 0, so they're not included in that cluster. So I'm very high on sparse principal components. You can also do redundancy analysis to predict each variable from all of the other X's. It's more of a useful descriptive tool than an actionable result, but occasionally it will help you do a data reduction. Tim is asking the key question, which is, are you losing interpretability of variables using principal components? I think you somewhat are. And, there's a contest between interpretability and predictionability. The more interpretable something is, the less well it predicts. And that's just the way things work in statistics. So it's kind of a Maxwell's demon problem. And there was a section we skipped over that goes through Maxwell's demon analogy. we can try to interpret the principal components by relating the original variables to the components. So you might do a stepwise regression to predict the first principal component from all of them, all of the variables, and then to predict the second component from all the variables. That's just a descriptive analysis to help you understand what the principal components are representing in the data. Make them a little more interpretable. But this is one of my favorite ways, which is variable clustering. And let's see, let's look at an example. Let's see if I can get to the right spot. So this is variable clustering on a bunch of variables in a diabetes screening project. And what we're clustering on is a similarity matrix, which is Spearman's rho squared. This is on page 11-27 in the notes in the PDF. So this, when you're doing variable clustering, instead of observation clustering, instead of having a distance matrix, you have a similarity matrix. So it's based on your correlation matrix squared. And you see that your body mass index is most correlated with the waist circumference of the person. Your weight was most correlated with your arm circumference. The BMI and waist were correlated with the weight and the arm circumference. This is all unsupervised learning. Now, how did these variables correlate with these variables? That's this level. So what is that number there? That is the average of the correlation, the rho square between this and this, this and this. And you average all those rho squared, and that's this value. So it's kind of a cross correlation between these two groups. The tricep skin fold thickness was most correlated with the subscapular skin fold thickness. Being a female was somewhat correlated with the length of your leg, their long leg bone, and that was somewhat correlated with your height and your length of your arm. The height was most correlated with the length of the arm, interestingly enough, not the length of the leg, big leg bone. So this is how you can envision how the variables group. And if you had some very high similarities here and your sample size was not very big, you would be combining these using principal components or some other method that came up with a single number. The smaller the sample size is, the more combining you have to do. This particular sample size was over 4,000 people with a continuous outcome, so we don't really need to do that much combining. But I think variable clustering is also good for understanding your data. So this is a general purpose method that is, to me, very widely applicable. And we may see more of that in a case study. Anybody have any questions about data reduction? So just to distinguish that from the way most people run regressions, they might do stepwise regression to try to get rid of variables. And the problem is you're getting rid of the wrong variables. Whereas if you do data reduction, you're not getting rid of variables so much, you're forcing variables to be combined with each other. That's what we do most often with data reduction. So it's a completely different approach. And when it doesn't work in a way that biases your R squared, because it's not, the Y variable is not available when you're doing the data reduction. All right, so that's a crash course on data reduction.
Just a
And
question,
yes.
how do you apply the clustering to put it into the model? Are you using the centers? That's
Yeah,
the Joy Yang.
Yes, occasionally you'll see clusters where it works to take a representative single variable from each cluster. That's not normally what works best, but it can work. And other times we had one paper where we got the clinicians to actually come up with the weights to create cluster scores using integer weights. That was one of the most satisfying ones we ever did. In other cases, we just let principal components combine the variables. Each cluster is fed in and we get the first principal component from each cluster.
And then there's comments about how you communicate the results of your model to probably to the non-statisticians.
Yeah, if we had time, we could go through that paper from the 1980s where the clinicians actually derived the clusters. That was one of the most wonderful ones I ever worked on. But other ways, we have indirect ways to help, like what does the first principal component mostly correlate with? It mostly correlates with your age. The second principal component most correlated with your weight, or maybe it was weight and age combined or something. So you can just give people descriptions about what the components are correlated with. It's not a perfect description, but it does help. All right. So there's a section about improving practice of multivariable modeling, and Sandra Greenland, the great quantitative epidemiologist from UCLA, has this paper from 2000. That's one of the best papers I've ever written. Not written, I would have written one of the best papers I've ever read. And I really encourage you to look at that paper. And then there's a summary of strategies. There's 3 strategies. There's strategies for prediction, estimation, and hypothesis testing, and they're not that different. But this gives you a default strategy. And it doesn't mean that it's the perfect strategy for you, but it's more of a checklist to get you started. And you might reorder some of the things. The number one thing about this list that's useful is it gives you things not to forget to think about. So you may find you don't need them, but at least makes you think about it. So there's a lot of data issues. Formulating good questions. Questions are better than hypotheses. So I wish I had said formulate good questions here. Don't use the Y variable to decide which X's to include. That relates to stepwise and univariate screening. Missing data has its own challenges. For each predictor, specify the complexity or degree of nonlinearity that should be allowed. This is what we went through with the saturated model, learning from the saturated model. That helps you assign fewer knots to variables that have low predictive potential. Do data reduction if needed, or use penalized estimation. So penalized estimation is a beautiful thing. It's a little bit challenging and it's not implemented for every possible model. Data reduction is a more general thing that applies to every possible model. Unless your sample size is very large, use the entire sample in model development and do highly structured testing to simplify the model if you really want, but the key is highly structured. So what does that mean? Test an entire group of predictors with a single chunk test. You get a single p-value and you decide to exclude the entire chunk or keep the entire chunk. If you pick and choose which variables of the chunk to keep, you're doing stepwise variable selection. So getting rid of a whole chunk or keeping a whole chunk is so structured that it eliminates a lot of the model uncertainty that is what is the problem with variable selection. You can use AIC to a limited fashion. You have to deal with additivity and interactions. You need to look at overly influential observations sometimes. Check your distributional assumptions, such as normality. You can do limited backward step down if parsimony is more important than accuracy, but you might need to use the bootstrap to penalize for doing that. So that's your model that you're going to interpret and the model you're going to validate. And the exception to all of this is if you had 100,000 people in your model, in your sample, you could afford to do some holdout sample for validation and simplify and not have to use the bootstrap. Just generally speaking, when the sample size is less than 20,000, you don't want to use a holdout sample because it's not very efficient. It's too noisy and it's too subject to the luck of the split. It's some more steps, but those are the key steps. And then you'll see not much different for estimation, not much difference for hypothesis testing. So does anybody have any sort of global strategy questions?
So, you're moving to Bayesian. Does that eliminate some of the issues with the inflated p-values?
Yeah, Bayesian has a much different way to think about this. So instead of looking at a model and possibly considering submodels, typically what you do with Bayes is you're going to have a model pre-specified, but it's going to be a bigger model. And then you're going to have a prior distribution that says, we're going to put a lot of emphasis on additive effects, and we're going to put skeptical prior distributions on interaction effects. And we're going to put moderately skeptical prior distributions on nonlinear main effects. So with Bayes, you can say, we're going to use prior beliefs and prior knowledge to emphasize some parts of the model more than others, and the ones that get more flat priors are going to be not discounted. They're going to be trusted. But by thinking about it in advance and having prior distributions for different parts of the model, that is how you bring subject matter knowledge and stability to the process. And you can also have prior distributions that are very spiked, like the lasso, but not quite the lasso. And by having spiked prior distributions, you could say, well, our prior knowledge is there's a very high probability that a lot of the variables are completely and utterly irrelevant. And so our prior distribution is going to have a spike at 0 such that those variables are going to get 0 coefficients in the Bayesian posterior distribution. Some of them will be. So you can put your prior knowledge about the population of regression coefficients and how likely they are to be exactly 0. So there's a lot of things you can do with Bayes. And the other thing about Bayes that's very important is everything we do with missing data is ad hoc when we're not using Bayes. And Bayes has a very formal way to handle missing data without using imputation. So it's more of a full modeling approach that is what we need to be moving to. When we're doing multiple imputation, there's just too much ad hoc and too many decisions that we're having to make that we're not well informed about. And Bayes gives you the more systematic way to handle complexity such as missing data. So that's some of the Bayes issues in a nutshell.
Thank you.
So when we get into model validation, this is a big chapter and we can't really do it justice. I'm just going to give you some highlights, but we have ways of describing the model. We don't do it with standardized regression coefficients. That's not really a good idea. We need to connect variables, so we don't want to do what SAS does, where it'll give you the effect of increasing age squared by 1 unit, holding age constant. That's not possible, but SAS will give you that output in terms of odds ratios and things like that. We need to account for nonlinearity, interaction, and meaningful ranges. So we can do things like interquartile range odds ratios. That is one approach. But what we really want to do is partial effect plots. So when we look, and let me just make a mark so I can come back here. So when we look at this example, that I think we may see this from a case study. These are partial effect plots. These are one of my favorite things to do with a model when it's mainly additive. You have to make special plots when there's interactions, but this is the scale of the predictor is here. This is the scale of the linear predictor when you combine effects. So in this particular model is a survival time model such that what you're modeling is the log of the time until death. So if you anti-log this axis, you will get the median survival time. But this is the log of the survival time as a function of each variable holding all the other variables constant. So when you vary only this variable and you hold all of these at their median, that's what you get here. So that's a partial effect plot with confidence band. This is a stronger variable. So this variable had 5 knots. So it had a lot of potential. So it was given a lot of opportunities in the model, had 4 parameters. So it has a chi-square of 16. That's telling you what's the evidence this is not flat. So we have some pretty good evidence it's not flat. We've got reference values here. That's why this has a 0 width confidence interval. But that is the age effect. It's fairly linear. This is the serum creatinine effect, which is very nonlinear and very strong, very steep effect here and here. Heart rate, mean blood pressure is very strong and very nonlinear. That's a very steep relationship. So these people are in shock over here. So you have your chi-square chunk test for flatness, and you have your shape of the relationship if you moved that variable but held all the other variables constant. And then for your categorical variables, you get things like this. The scale is just rotated. So log survival time is here, and the categorical variables are here. So that's a partial effect plot, and that is that's one of my favorite plots for showing a model. And when we do the case study, we'll get to some other plots. But such as nomograms. This is a lot of material about performance measures. There's mean absolute prediction error, mean squared prediction error. There's just everything under the sun. You can go crazy with all these measures. You can have the concordance probability, which is an ROC area in the binary Y case. You can have R squared and adjusted R squared, Breyer score, discrimination, calibration measures. It's the sky's the limit. Don't know where to stop. And then the bootstrap is one of our main tools for validating models, especially when your sample size is less than 20,000. The cross-validation is also a good method. The bootstrap is a little faster and easier to program. And the bootstrap exposes the problems with stepwise regression better than cross-validation does. So bootstrap involves sampling with replacement, and there's a lot we wish we could get in today, but I just want to leave you with one thought about what we use the bootstrap for. Is we're using the bootstrap for model validation, which is not using it for a confidence interval like we often use it, but it's using it to estimate bias. So bias is important when you're looking at model validation, because one of the things we want to measure the bias of is R squared and ROC area. So if you get an R squared of 0.7, but you did data mining and all kind of double dipping to arrive at the 0.7, the bootstrap might tell you you're biased by 0.2, and our unbiased estimate is 0.5. So we use the bootstrap to estimate how biased the R squared is, how biased the calibration curve is, how biased the ROC area is. And that is why the bootstrap comes into play. There's a lot of discussion about what model validation really means. You could spend days and days talking about this stuff. My working definition of an external validation is validation of a prediction tool on a sample that was not available at publication time. If it was available at publication time, you probably should have used it in your training data to get a better analysis. So there's many, many aspects that we could discuss and debate about validation. Please read this when you have time. You have to decide which quantities to validate, like R squared. You have to know why data splitting is a bad idea unless you have a 20,000 patient sample. Why is resampling better than data splitting most of the time? This is tenfold cross-validation. So I think we're going to show this more in the case study. So I'm going to skip over a lot of stuff. This is what I wanted to spend a little more time on. This was the second demonstration about variable selection and variable importance. So the idea is when you have a lot of candidate variables, people are using random forest, and then they're learning that it's nice to be able to judge, since the random forest is a true black box that's totally uninterpretable, it's nice to know at least how much did a variable matter in the way that the random forest formed a prediction. So that would be a variable importance measure. And random forest tends to have a lot of overfitting, and people are using random forest when the sample size is not large enough. And ironically, when the sample size isn't large enough for a method to be used reliably, it's also not large enough to tell you if the method is working reliably. And it's not large enough to calculate variable importance. So people are calculating variable importance, but they're not putting confidence intervals on it. So if you put confidence interval on variable importance, you'll find out that we don't know how important a variable is to a random forest, unless the sample size is pretty darn big. So what we're doing is putting confidence intervals on the variable importance using the bootstrap. And this is going to also put in context the real problem with stepwise variable selection. Stepwise variable selection is just like the lasso. They're unable to tell you which variables are important. They're unable to tell you the right variables. So we can quantify that with a bootstrap. So we're going to get confidence limits for the rank of each predictor. And the rank could be based on a t statistic, f statistic, r squared, partial chi-square statistic. It could be any statistic you want. So in our example, we're going to form 12 predictors. They're all random uniform distribution. And this is our true linear predictor. So our sample size is 300, and we have a high signal to noise ratio situation. And the variable importance is equal to the subscript of the variable. So x1 has a weight of 1, x12 has a weight of 12. So the importance of x sub I is I, and we have a random error with standard deviation of 9. We're going to fit the model, and we're going to do 1,000 bootstraps, and this is very easy. So we're going to set aside the ranks of the variables. There's 12 variables to rank, and we're doing it 1,000 times. So we've got a 1,000 by 12 matrix of ranks. And the way you rank a variable is you say, give me the ANOVA of the fit. Don't sort it by the chi-square because we want the same variable to be in the same position every time. Don't plot the result. We're going to pass that to the plot method, but don't actually plot it, because the plot method will return the chunk test for the variables. Chunk test is an overkill here because it's only one coefficient per variable, but we're going to get one statistic per variable from the partial contribution to the model, and then we're going to rank those, and then we're going to do this rank varies for every fit. I'm going to do that 1,000 resamples. And now we're going to get the 0.025 and 0.975 quantiles of the ranks. So that's going to sound like a lot of gibberish. Let's see what it actually looks like. So what happened was the variable that's weakest is X1. In our sample of size 300 subjects, X1 came out the second weakest. X12 is supposed to be the strongest, and it came out the 4th strongest. So that's not correct. That's not correct. That's what happens with random sampling. The variable that came out the weakest was X3, which was supposed to be number 3. The variable that came out the strongest was X9, which is supposed to be over here. The confidence intervals all contain the true ranks, luckily. But the width of these confidence intervals expose totally the difficulty of the task of telling you which variables are important. So the variable that is apparently the most important, which is the wrong one, X9, the data are consistent with it being the eighth weakest to the strongest, the 5th strongest to the strongest. The one that was really the strongest, the data are consistent with being the 5th strongest to the strongest. So this tells you the limit of our ability to determine which are the winners and the losers. And this is in a situation where the X's have no collinearities whatsoever. If you have collinearities, everything gets much, much harder. So look at the width of these. This is with 12 candidate variables, 300 observations, and we still have a very tough time saying what's a winner and what's a loser. So we did this same example where we had 220 candidate proteins, and we ranked the variables by their Cox model statistic, ability to predict time until death. And basically what we found was the winning biomarker out of 220 candidate biomarkers, all we know it's not in the 120 losers. The data couldn't tell you if the winner is really a winner. It just told you out of 220, it's not in the 120 weakest markers. That was the limit of what the data, the information in the data has. So the beauty of this thing, this exposes the difficulty of the task. How many variables are competing against each other? And it exposes the difficulty of the task. What's your sample size that you're trying to do this with? So you can see these confidence intervals for variable importance are broad enough that you can predict the instability of stepwise variable selection using these importance measures to select variables. It's going to be very problematic. Any questions about this sort of thing? Question? Let's see, I'm looking back. I see a question by Dave. In rare disease with very small prevalence, would you also avoid training test split and rely on the bootstrap? Yeah, the question about when to use the bootstrap versus to use split sample validation is based on the effective sample size. So the case where I did a split sample validation with 17,000 patients, that was with a binary outcome where the death proportion was 30%. So 30% out of the 17,000 died. And that's a pretty rich sample, and data splitting failed. It was unstable. But the sample size you need for these things depends on the nature of the dependent variable. How continuous is it? And I think if you had a continuous variable, you would not need 17,000 observations to split the data. But I would still mainly do resampling because resampling exposes the volatility of the final model that you're gonna write up. If you do split sample validation, it doesn't expose any of the volatility of the model that you get from the training data. So I still like the resampling idea for a lot of different reasons. And then Max asks, is it important to consider an option to implement data reduction as part of the model tuning? And I don't know exactly what model tuning means in that context. Max, do you want to speak up and say anything there? Well, if you want to add anything to that, Max, type it in. Let's see. Dale asks, so you don't use k-fold cross-validation unless n is 20,000? No, I wouldn't say that. I don't use data splitting unless n is greater than 20,000. I would use 100 repeats of tenfold cross-validation for any sample size. And you know, you can't do cross-validation just once, like tenfold. It has to be repeated lots of times to be stable. So you're fitting a lot of models. It's a very computationally expensive thing to do. If your sample size is very big, you don't need to do 100 repeats of tenfold cross-validation. You might need to do 10 repeats. So the number of repeats you need is going to depend on the sample size. But if you repeat it enough, cross-validation is going to work really well. Joyce asked a question about data reduction. If you're using observation clusterings to do data reduction, would you use cluster centers instead of original data points? And I think the key thing to know there, you really hit on the key thing, Joyce, which is a lot of people are doing clustering and then they're actually forcing observations to be put in clusters and they're totally forgetting what the distances were. That's really a terrible idea. So when you're doing observational clustering, you need to use the distance from the cluster centers as your variates. Just identifying someone as being in a cluster. If the cluster is a single point, that's going to be fine, but clusters are not single points. You're going to put somebody inside a cluster and not tell us where they are. You're just going to classify them as being in that cluster. And that person who's over here might actually be more like people in this other cluster. So if you record how far from the cluster center each observation is, you'll have the metric that you need in your modeling. But people are taking the easy way out and they're just using the cluster identification, which is a forced classification that's going to ignore how tough a call it was, or were you near the edge of the cluster or near the center. All right, so really good questions. So make sure you understand this idea of bootstrapping ranks, because I think it's a very general issue that needs to be used a lot more often. So other stuff in the notes, there's a lot more about validation. There's let's see. A lot more about bootstrapping. Then there's a chapter on the RMS package and understanding the R modeling language. And then there's a lot of big case studies that go into tremendous detail. And we're just going to go through one of the case studies, which is in chapter 12, is a case study of parametric survival modeling. So this is where we had a random sample of 1,000 patients. These are patients with a 6-month life expectancy. They're mostly in intensive care units and they're older adults. It's a data set that's readily available and it's a great teaching data set. So we're going to analyze the acute disease subset, which is just over 400 patients, acute respiratory failure, multiple organ system failure, or coma. And patients had to survive until day 3 of the study to qualify. So the follow-up really starts on day 3, which is when our baseline measurements are. So we're going to do some descriptive statistics. So you'll see here that the describe function, when you pass it to LaTeX, it will give you this output, or you say HTML, and you'll get the same output in HTML in your R Markdown report. So it's a good way to look at descriptive statistics is to have these spike histograms showing you the whole distribution of each variable, and you'll see why that's important in a minute. And then we have 537 patients, not 400 something I said a minute ago. You see this variable has information value of 1. So that's a very continuous variable as full information. The mean age was 60.7, the median was 63.7. This is the whole distribution. The death variable has information content of 0.67 because it's a binary variable that's not even perfectly balanced. So that's the information in a variable relative to a continuous variable that's based on that sum of cubes formula that we had. And so you're going to have lower information in a binary variable. So when you look at some of these distributions, you'll see things that box plots would not show you, which is look at this distribution of mean blood pressure is very bimodal. So that's because the blood pressure that's recorded is the worst blood pressure in a 24-hour period. And your worst blood pressure might be too low or it might be too high. So that shifts you away from the middle and creates a bimodal distribution. So what we have is a lot of physiologic variables and some demographic variables, and we can use that to predict survival time. And you can see that some of these patients had, like they had a heart rate of 0. Those are real numbers. And they had a blood pressure of 0. These are people that had a cardiac arrest. So they had to be resuscitated. So when you have cardiac arrest, your blood pressure and heart rate go to 0 for real. So that's not dirty data. So those are descriptives. And then we look at some clustering of missingness. And then we look at clustering of the variable values. The clustering we're using is not Spearman's row, which I tend to prefer, but this is using a more general measure of independence. So this is the clustering of missingness of the variables. So these variables tended to be missing together on the same person. And then this is a clustering of how the variables relate to each other. So the variables are not strongly related to each other except for these two measures of kidney function, which makes a lot of sense that they're going to be somewhat redundant. You don't really need both of these variables maybe in the model. So the next thing we look at is distribution assumptions. And you know, people do things like stratified Kaplan-Meier estimates and looking for parallelism on a certain scale. And that's not really a very general way to think about it because these don't look parallel. They don't look like they're fitting a log normal survival model, but this is not adjusted for any covariates. So what we need is a way is to have a parametric survival model. This calls the SurvFit function in the survival package, makes it a little easier to use. The distribution is a log normal distribution. And we're going to have the disease group, a spline of age, and a spline of blood pressure, just 3 variables. Because when we take this log normal survival model and calculate residuals, this S is made up of the survival time and the event censoring indicator. It's a 2-column matrix for time until death. When you calculate residuals off that, when somebody didn't die and they were censored, so their time to death is going to be something in the future, the residuals that would create right censoring, and the residuals are right censored. And so when you have right centered residuals, you can put the Kaplan-Meier estimate of the residual distribution and see if it has a normal distribution. So that's what we're doing here. We've taken the residuals from the parametric survival model and we've stratified them by disease group and calculated the Kaplan-Meier estimates of the residual distribution and plotted that against the theoretical normal distribution, and they kind of hover around that. Likewise, when you divide by quartiles of age, and you get Kaplan-Meier estimates for the residual distribution, those hover around the normal distribution. Same for blood pressure. And then this is stratified by a random number. This is a good trick to use in data analysis. When somebody says, is this meaningful departure from the model assumptions? Well, if we stratify by a random number, so here's where we calculate it, and we're going to stratify by a random number. So a random number has to fit the model. You could never have a lack of fit due to a random number. So if you still get a little bit of lack of fit due to a random number, you know that's just sampling variation. And that sampling variation is similar to this sampling variation. So that tells us if we want to argue not to worry about the log normal assumptions, we're probably not going to get anybody to argue with us. So this is where we use one of the methods to gauge the potential of the variable. Now I'm actually going to skip to a different rank correlation measure. This is not the one we studied. This is a separate correlation of each variable with time until death. We're going to rank those correlations. And the variable that has the highest potential is mean arterial blood pressure. So we're not going to make that variable be linear. The continuous variable that has the lowest potential, this is absolute rank correlation with survival time, is temperature. We're going to force that one to be linear. And then we're going to allocate degrees of freedom in descending order going down here. And we also do a redundancy analysis. So we're going to use every variable to predict every other variable. We're not going to use the outcome variable. So this is unsupervised learning. So this is the redund function in the HMIS package. So you can see from this, the R squared with which each variable can be predicted from all the other variables. So the variable that's easiest to predict is disease group, because it has a lot of overlap with the coma score, because one of the disease group members is coma. So these are kind of redundant. The variable that's second easiest to predict from the other variables is coma score. It's being predicted somewhat from this. But you don't really see any truly redundant variables here. If one of these variables had an R squared of 0.98, you probably don't need it in the model. But this is the better approach for gauging the potential. This is the one we did go over. Allow all the variables to have the maximum number of knots that we would think we can get away with, which will be sample size dependent. And we're going to fit a saturated model, and we're going to plot the ANOVA. So we're going to use a quadratic for a special variable here. It's a count variable. But otherwise, we're going to have K knots where K is 4. And this is the result. So the variable that has the highest potential is disease group. So that's categorical. We do not want to combine its categories. The variable that has the next highest potential is serum creatinine, kidney function. We do not want to make that one linear. We don't want to make that one linear or that one. But temperature, as before, is going to be linear, and race looks so irrelevant that we could make sure we don't use more than, say, 2 race categories. That's how you would reduce the parameters for a categorical variable. So this is a way to measure the potential that a variable has so that you don't give a lot of knots to variables of low potential, but you have to be conscious of what this does not reveal. It doesn't reveal the actual shapes of the regressions. So we could be simplifying the wrong variables here. It does reveal the total association. So if you said from this, I'm going to take sex out of the model, you have broken a promise. So by analyzing it against the outcome variable, we have promised to keep it in the model no matter what, even though the chi-square is almost 0. So now we're going to use that, and we're going to have the number of knots is going to be kind of in descending order according to that dot chart. So this is our model. It has fewer parameters in it. This is the likelihood ratio chi-square statistic showing a lot of evidence that there is some association somewhere. This is the number of subjects. This is the number of deaths. This is the standard deviation in the log normal survival model. And we have some new R-squared measures here. And there's a web page that explains all these. This is the R-squared that has always been in the package. And then these are new R-squared measures that I have a lot of excitement about. And this is the one that is an adjusted R-squared. It adjusts for your having 30 parameters. So this is going to, you see how much lower this is than that. This is going to penalize you for overfitting. But it's taking the effective sample size to be 537, which is this. This is taking the effective sample size to be the number of events. Now this is going to be a better way to do it than that, because a lot of the censored observations don't contribute a full observation. So this is the R-squared measure that I'm liking the most. So we're using, in how you adjust for the 30, instead of using the full in the adjusted R-squared formula, you're using the number of events, which is our effective, roughly our effective sample size. So you get a 0.441. This is a rank correlation measure. You get all your spline terms that you could never interpret. You get your ANOVA, which we already looked at something like that. But this is what we also looked at. This is the partial effect plot. So we're going to, when we say predict of the fit, we're going to set a reference thing to be in common over all the variables. When we say predict without telling it which variables to vary, it's going to vary all the variables one at a time. So this function does a lot of work for you. And then it passes it into a ggplot method. And there's also a plotly method if you want an interactive plot. So we saw this before, partial effect plots. And this is our ANOVA output. So we start here, we have evidence for something. We have evidence of things being nonlinear. And we have the nonlinear effect of individual variables. So serum creatinine had a very non-monotonic effect. So it has a huge amount of nonlinearity in it. So this is the overall chunk test for creatinine, and this is the chunk test for nonlinearity of creatinine with two parameters versus 3. So the ANOVA function tries to figure out which chunk tests you might be interested in. It gives you all of them. You get a lot more if there's interactions. This will give you things like odds ratios and hazard ratio charts, but here it's a survival time ratio. Oh, this is the plot of the ANOVA. These are the survival time ratios. So if you vary age from its first quartile to its third quartile, you cut your survival time in half. So by being in the intensive care unit at age 48 versus 74, 74-year-old has half the survival time of the 48-year-old. In other models, these will be odds ratios or hazard ratios or differences in means. Then we're going to do an internal validation using the bootstrap. So that is the validate function in an RMS package. We're going to do only 120. It's not really enough. But this is what a bootstrap validation looks like. You get your rank correlation or R squared in the original sample. And when you take samples with replacement using the bootstrap, the R squared actually goes up because the bootstrap is duplicating some observations. And when you freeze the model and apply it to a test sample, it's 0.46. So the optimism on the average over 120 repetitions is 0.05. That is our estimate of the amount of bias in that. And so when we take this and subtract it from that, here's some round off not shown here, you get a 0.44. And you also get some calibration and other measures. So we're estimating the model was overfitted some, and the slope of the calibration curve is estimated to be 0.9. So we, roughly speaking, say 10% of what we learned from the data was pure noise. Then we're going to do a calibration plot, and we're going to try not to bend the data, which is not a very good way to do it. We're going to do it with a continuous plot. And that's this blue line. So the blue line is our best estimate of how the predicted survival probability relates to the actual survival probability. And you can see there's a little bit of overfitting because this is below the 45-degree line here. And so, but it's not bad. And if you stratify and got Kaplan-Meier estimates, they're just too unstable to know anything about. So that is our case study. And before I show you one other thing, I want to see if there's any questions we need to catch up on.
There were some other questions, and then I have a question.
Why don't you go first?
Okay, 120 wasn't big enough for your internal validation. What would be big enough, and how would you make that decision?
Yeah, we don't really have a good paper that tells us exactly how many bootstrap samples to do, but I tend to do 300. I just let it run just a little longer. And this, I don't know why I didn't do that here, but 300 is kind of the minimum. And now if your sample size is really large, you often don't need 300 bootstraps. But just think of 300 as a good general number.
Okay, and then there's two other questions. Gabriella said, for multivariate response, you might want to finish your case study here. And then the other is using observational, how to use the observational clustering to predict on new data.
Yeah. So how to use observational clustering to predict on new data? Was that the question?
Right, that's Raul.
Is that under the chat or the Q&A?
That's in the Q&A. It's at the top, I think. How do we handle using observational clustering to predict on new data?
Yeah, I think it's actually kind of difficult, but I think if the way you coded the variables was distance from cluster centers, and you used the cluster centers in your original data set and you kept those so that you could always calculate the distance from the cluster centers in new data, just like it's a covariate, I think that would come close to being reasonable.
That would be new clusters in the new data.
Now you're using the clusters that you found on the old data.
Okay, using
and you're
their
saying
centers.
How close was a new observation to the center of each of the clusters in the old data?
Yeah.
And then the regression coefficient for those distances would capture the relationship with the outcome.
That sounds good. So Gabriella was wanting to know about multivariate responses.
Yeah, that's a good challenge. And the one that we deal with the most is when it's longitudinal. That's a specific kind of multivariate. I don't know if Gabriella is talking about a different kind, but when it's truly multivariate, like you're analyzing systolic and diastolic blood pressure jointly, there's some classic methods for doing that we don't tend to use very much anymore. But the notes go into a trick that sometimes you turn everything backwards and you use the multivariate response to predict a univariate baseline variable with like a logistic model. So sometimes you can turn a multivariate problem backwards in terms of X versus Y and make it a univariate problem. That's the easiest way to deal with multivariate, but that only applies to a small number of cases, a small number of situations. So there's a lot of other things we need to worry about with multivariate data.
One new question from David. Clustering variables should not be confused with clustering observations.
Right, totally different. To me, clustering variables is more direct, because when I have multiple ways to measure the same thing, I'm just creating a new variable for each person, and then I'm relating that new variable, which is like a score. I'm relating that new variable to the outcome, and I have a very natural way to form predictions. When I'm clustering observations, it's not really respecting the variables as directly as when you're clustering variables. So it's more of an indirect way to do it. All right, be thinking of other questions. And this is just to close out. You can say LaTeX of the fit, and you see the whole model here with all the splines written out in simplest form. So not the most beautiful thing to look at, but it's about as simple as you can make the math. And then you can make a nomogram. So the thing about a nomogram is you're plotting the model, but you're also plotting a lot of extra axes. So what we can do is we have our predictors. You notice serum creatinine had a U-shaped prediction. See how it wraps around the axis there? So that's a non-monotonic relationship. Age was fairly linear. Heart rate, we made it to be linear, I think. And so what you're doing with a nomogram is you're taking every variable and bringing in its regression coefficients, and you're creating an equivalence on a 0 to 100 scale. So you're going to score every variable according to its regression coefficients and put those on a common scale. And for every variable, you add up how many points this was. So somebody who's in this disease category gets 40 points. Somebody has a mean arterial blood pressure of 40, they get like 58 points. So you add up those points on this scale, and then this tells you the linear predictor for that person, X beta hat, and you can quickly convert that to other things like median survival time and mean survival time. You could also add an axis for the probability of living 1 year, 2 years, 3 years. So when you're doing a nomogram, you make it really intuitive how all these things combine into giving you multiple different types of predictions, like on the time scale versus the probability scale. And you can add as many axes to a nomogram as you want. Can you tell a story where developing a model led to a true discovery, unexpected relationship? We've seen a lot of things like that where the relationship between, say, a lab value measured from the blood and the patient outcome was totally unexpected, and the clinicians had been oversimplifying it for a long time. And one of the things we learned about modeling is people make various assumptions that they never test. And with careful modeling, you can undo some of those assumptions. So there's examples in the course notes about this predicting whether somebody has meningitis or has bacterial meningitis. And one of the things we uncovered is the clinicians were using a certain blood parameter, which is the relative number of polymononuclear leukocytes. I think it's the full name of it. And they thought the percent of cells that were in that type of cell was the way to help diagnose the patient. And we showed that they've been normalizing by the total volume of cells all these years, and that was not very relevant at all. What mattered was the absolute number of cells. So we uncover not just ways to predict, but we uncover how the variables relate to things. And we uncover that the way someone was scaling a variable, it should have been used absolute and should not have been normalized. You discover a lot of stuff like that. Another one is people think that body mass index is a good way to model height and weight. And when you analyze data, you find it often doesn't work. So one of the coolest examples was a PhD epidemiology student at Vanderbilt showed that what predicts your LDL cholesterol is not your body mass index, and it's not your weight, it's your height. So the weight is irrelevant. What predicts your LDL cholesterol is your height. So by modeling, you learn that what is giving weight to the outcome is often different from what people think. So we have a lot of stories that are kind of like that one.
So don't forget to read all the kind words, Frank, in the chat. This has been absolutely amazing. And I'm amazed at how much you've changed things and new things. Just wonderful. Super.
Well, I appreciate all those comments a lot. And I want to show you something that's kind of new and semi-cool. So I just need to share a different window here. Oops. So I think you can see this R workflow. So this is really kind of hot off the press. And this puts things into a different perspective, which is mainly about using R, but it also has a lot to do with all the things you do when you're not modeling, but you're doing descriptive statistics. And so first of all, how do you import and annotate data, and how do you check data, and how do you describe how your sample came to be? And then how do you recode, transform, reshape, merge, aggregate, manipulate? And a lot about descriptive statistics and analysis with just real general ideas, but these are mainly descriptive analyses. So this book is mainly about this. It's not about the formal analysis, which is what we were mainly doing today. And then there's some stuff about speeding up computations and how to do simulations. But I just wanted to go through this one on analysis here, because when you get into formatting, there's something that relates to what we're doing. So this is using Quarto, which is the replacement for R Markdown that I hope many of you are going to start using. It's really ready for prime time, and it's really amazing, and it's very compatible with your syntax for R Markdown. But this is a section on formatting analyses. And so this is using the RMS package that says that the output that can be specially formatted is going to be in HTML automatically, not in LaTeX or plain formatting. We have to use data disks to save the characteristics of our independent variables for RMS to work. We're going to cube root transform one of the variables. So this is a logistic regression model to predict the probability of patient dying in the hospital in this support study that we've been analyzing. So you have splines in these variables, and this one is a spline in the cube root of serum creatinine that makes it behave better. So when you get your output, it's what we've been seeing, except this is a binary logistic model with these, you've got these new R squared indexes, and this is ROC area or C index and so on. You've got these spline terms, but we can say, make this a pop-up note. So that'll put the ANOVA in a collapsible note, and you click there and you'll see your ANOVA. But the thing that's a little neater is you just make a little function that's called RMS display, where your input here is your fit. Like this fit object was created right up here. That's F. So the RMS display is going to be taking the fit that we had, and then we're going to make a bunch of tabs in our report. And so the first tab is going to be empty. So it's a tab down here. You see it's an empty tab. And the reason for having an empty tab is so that you don't show any of these other tabs until they're on demand. So that just makes the default show nothing. And then the first real tab is to show the model output. The second one is to show the output of specs, which is the telling you where the knots are and where the ranges of the X's are in long format. And then that's going to be using raw output. So that just says this tab output needs to not assume it's HTML. It's just going to be raw output. This is going to be a LaTeX output from the model fit. This is going to be ANOVA plus the plot of the ANOVA all in one tab. This is going to be the odds ratio chart. This is going to be the partial effect chart and the nomogram. So when you run RMS display on that fit object, it automatically puts all these tabs in your report. So this is your model, like we already saw. This is our specs. So this is showing the label of the variable and the number of parameters the variable gets, what was assumed about the variable, was there a pre-transformation, cube root, and then where were the knots placed if it was knots. So you have your knots here. And now these are ranges for prediction and for plots. And then when you do your equation, you get your result of LaTeX. And your ANOVA contains both the table and an interactive ANOVA where you can, not very impressive when you have only 3 variables, but you can hover to see details. That's using Plotly. And then your odds ratios, you can hover to see some things, and you can look at different levels of confidence. So you're at 95% confident level, but you want to add in the 99 and the 0.90 confidence, and we want to remove the 0.95. So you can click to show different things. And then the partial effect plots and the nomogram. So you can sort of make more stuff than you think you need, but just put them away in tabs in case you do need them when you're showing the report to somebody. So this this R workflow document goes through a lot of ways to make reports flexible and use the new capabilities. Like Gordo makes it really easy to put marginal notes, and you can also do marginal plots. So I think I have, nope. I think that's under analysis. So you can put little tables in the margin if you want to look at details. And sometimes you can put more than that. So Quarto just makes these things so easy to do. Here's a ANOVA in the margin if it's not one you're mainly interested in, but you want to be able to zoom and look at that. So the other thing about this, when you get into data manipulation, there's all these things like reshaping data and adding and changing variables and just manipulating the data set in general. And that gets to be more interesting when you start manipulating longitudinal data. So the reason I bring this up is if any of you are not introduced to the data table package, you really need to be introduced to it because it is a life-changing event to start using data table instead of things like the tidyverse. You'll find data table is really efficient in terms of your time. So I don't know if anybody's still there, but I think that pretty much wraps it up.
So there was a question, Frank, about data transformations. And then my question is, do we have a link to this R workflow document?
Yeah, that is, let me put that in the chat. I'm putting the link now.
Cool. And I forget who asked, but somebody asked about transformations. And there were still lots of this here. You have kept our attention very well. Thank you
Right.
so much.
Just put a link to the blog article about our workflow, which gives you an overview and more motivation. And it gives you a link to the electronic book that we just looked at. So was there a question about data transformation there, Madeline?